Well, welcome everyone. I think it's good that everybody's looking here and not at the better view outside there. It's a beautiful day, so it's good that you're spending time here talking about memory-centric computing. Let's say you can enjoy Chicago later. So we're going to talk about some things that are going on in memory-centric computing, specifically focused on what we have been doing in my research group. But I'll give you some overview of the field as well. Feel free to ask questions. It's a tutorial, not just a talk. So feel free to interrupt me anytime. We don't have to cover all of the material, and there's a lot of material to cover actually on this topic, especially today. I think today is a good time to be doing research, in my opinion, in memory-centric computing, processing in memory, processing in storage, processing in sensors and the network. That's what this is going to be about, I think. Although I'm going to give you an overview of what else is related to it to begin with. Does that sound good? Okay, great. So let's start. Let's start with that overview first. Okay. I don't know what's going on here. My computer wants to go to my web page because I clicked on it. Okay. So we're having a big problem with data in our computing systems today. I'm going to quantify this in this tutorial a little bit more. Somehow this is not working. Maybe I'm just going to stick to the computer. Yeah. Okay, I'll just ignore this one for now. Although it'd be nice so that I can walk. Okay. Basically, data is important workloads are all data intensive today, and data is really growing in those workloads. If you look at machine learning, genomics, video processing, or web processing databases, these workloads are all data intensive, and they require rapid and efficient processing of large amounts of data. And on top of this, data is increasing. We can generate more data than we can process today, and we want to do more sophisticated analytics on the data. Increasingly, humans are more interested in learning more, right, and mining more data. This is just one example. This is actually a nice talk that I would recommend to people. This person, Shanli, is the chief architect of Cerebras Systems. They're building these wafer scale chips, and their goal is to really accelerate machine learning training. And the reason they're building wafer scale chips is because they need a lot of compute and a lot of memory at the same time on the same chip so that they don't go off chip as much as possible. They have 40 gigabyte SRAM in their latest wafer scale engine, which is a lot, if you can imagine. 40 gigabytes is not enough actually for huge data sets, right? They still need off chip memory, but at least they don't need to go off chip for 40 gigabytes. But he gave this nice talk that this nice seminar that goes over what they're doing. But my point over here in this slide is to show that neural networks clearly are growing in terms of both compute demands. You can see that compute demands have been increasing 1800x in just 2 years, but also memory demands. Memory requirements are also here. So both memory and compute demands are increasing over here, especially for large-scale language models like this, as you can see. Now, you can argue that is this a good thing or is this a bad thing? I actually think that this is probably not a great thing that we're doing. We're just putting compute and trying to claim that there's intelligence in this. I'm not sure, frankly. We can come back to that later on. I believe this will get worse before it gets better. We'll figure out more efficient ways of doing that eventually, in my opinion. But I think data will grow regardless of whether we become efficient or not. And this is neural networks. Clearly, a lot of people are hyped up about it, but there are a lot of other interesting applications, clearly, like databases, graph processing, Spark type of applications, data center workloads. And people have shown that these are bottlenecked by data in terms of performance and energy. And if you look at the mobile end, mobile applications are also bottlenecked by data. These are some examples over here. By no means this is comprehensive, but we're going to look at these workloads actually a little bit more and show that they're bottlenecked by data. I'll talk about an application domain that is close to my heart. We've been working on this for some time now. And here, this is the genomics. Essentially, genome sequencing technology has evolved and developed so well that today we can sequence lots of genomes very quickly at high throughput. As a result, number of genomes that we have has increased significantly. And we are doing sophisticated analysis on it also. We're basically bottlenecked by how fast we can analyze the genomes. And I will point out this graph over here This is a commonly overused graph in genomics. I don't know why I cannot see my, yeah. Anyway, can you see my thing? I cannot see anything over here, but maybe I will. This works for this. Okay, that's good. It doesn't work another way, but it works here. So this line over here shows the cost of a transistor. Basically, Moore's law is reducing by that exponent over there. If you look over here, this is the cost of a raw megabase of DNA sequencing cost base. But you can see that it's reducing much faster than Moore's law reduces the cost of a transistor. And you can see the inflection points are actually introduction of new technologies. This is the high throughput sequencing technology, and this is the nanopore sequencing technology over here. So the technology has enabled us actually to sequence a lot more data very cheaply. And clearly this has many application cases, as we will see in a little bit. So basically, we have these sequencing machines that are very good at sequencing data. And we are limited by what we can do in scientific discovery and medical advancements because we need to process that data. And that data processing takes a long time. Now, if this was a tutorial on genome analysis, I would actually go into a lot of these steps, but it's not a tutorial on that. Therefore, I'll point you to some papers related to that. But I think this is an increasingly important field. Why? Because we can learn a lot by analyzing genomes, right? We can understand evolution, species, different people, how they react to different things. We can understand microbes. We can predict disease outbreaks. Clearly, these machines were used in COVID-19 significantly and develop personalized medicine that could be life critical in certain situations. Actually, there are very interesting works that show that if you can reduce the cost of sequencing and the time to do sequencing, you can potentially save some critically ill infants very quickly. Because at that point, 2 days, 5 hours, 1 hour matters actually. So there are cases where this is extremely critical in terms of life. Okay, so this is one of the sequencing devices. I call it the data generator. This is a great data generator. You can actually buy it for very cheap, almost $1,000, and you can sequence your own genome or others' genomes. But this is a terrible data analyzer. So this has no processing capability in it. So you have to move the data that it generates to laptop, but laptop is also not powerful enough. You have to move it to data center. And that's not what's done today. But you ship these all over the world so that you can gather some information. In fact, people are doing studies gathering, for example, taking swabs out of metros, subways, and trying to figure out what's going on in the microbiome environment of an entire city. People have done this in New York City, for example. They've done it in the world scale also. Clearly, this scales up a lot. But then you have to move the data somewhere, and usually people move it to data centers. So that's essentially what we're going to discuss in this tutorial. Are we doing the right thing by moving the data all over the world? Let's say that's a macro scale. And also within our machines, all across our machines, that's the micro scale. And can we do something about it? So if this device, for example, had good processing power, maybe we didn't have to move a lot of data all over the world. And this data movement, I think, we should think of this data moment as something costly, like in terms of energy as well as performance. And if you don't care about performance, maybe you hide the performance somehow. Energy is definitely there because you cannot eliminate that energy of the data moment, right? And usually we tend to ignore that energy, in my opinion. Okay, so I spent some time on this one. If you're interested, there's a lot of readings that are possible. And I think this is an exciting area of research. So this is another sequencing machine, by the way. This is the Illumina sequencing machine. It's a lot higher throughput, a lot more expensive. It's about $3 million, this machine. It's highly accurate. It's similar to a lot of nanopore machines, basically, the way I think of it. But these machines are very special purpose if you look at them. What we're doing today with our data generators is we have very, very special purpose data generators. We're feeding the data, moving the data to poor general purpose machines that are basically getting swamped with that data. I like this picture because this shows a mismatch between the data generation and data processing. It doesn't really make sense to throw a general purpose machine for processing data coming out of a very special purpose machine. And you can think of this as a genome sequencer, but this can easily be a video camera, right? All over the world. It could be clicks on the internet. That's another possibility. Basically, you can replace any data generator today with that one. And I think Because of that, we're overwhelmed today. So I'm not going to talk more about genome analysis. I find this fascinating, but we've written some articles. If you want to, for example, do research in this area, these are some beginner articles, if you're interested. Actually, we've written a longer version. We were invited to write this longer version of this article for this journal's special issue. If you're interested, this is a much longer version. And we cover a lot of interesting things. And feel free to provide us feedback. We're always happy to improve these. Let me give you one example of what we can do today by being closer to memory, if you will. So we've been looking at FPGA-based near memory acceleration. Clearly, FPGAs exist today, and also high bandwidth memory exists today. And we work together with IEDM so that we can offload some critical computation to an FPGA board that has high bandwidth memory. High bandwidth memory is essentially 3D stack or 2.5D stack memory that can provide very high bandwidth to the FPGA. And it can customize the logic in the FPGA to the application. In this particular work, we customized weather modeling, Cosmo weather modeling application, and genome analysis application. And basically, we see significant performance improvements. Sorry, I don't know why that's flipping. I'm afraid to touch it again. But if it becomes really annoying, let me know. So I'm not going to go into the details. The paper explains the details. Basically, you need to customize the logic to accelerate the application. And some of the benefit, of course, comes from the high bandwidth memory. The fact that this customized logic is having access to very high bandwidth of memory. And it's not limited by the CPU's main memory bandwidth over here that I cannot show. Yeah. And you can see that we see significant performance and energy improvements at the same time. So this is today. I think even today, by using relatively new but existing technologies, you can improve both performance and energy efficiency. And this is true for weather modeling as well as bioinformatics workloads in this particular case. Yes, please.
Is this a single fixed logic design for each program, or is the design being reconfigured throughout?
So this is, yeah, that's a good question. In this case, it's a single fixed design for the algorithm that we improve. But you could imagine the reconfigurability happening dynamically, but we didn't do that in this work.
So,
yes.
Question in this particular example, are you exploiting the full bandwidth of the connection? Or, I mean,
so that's a great question. In the paper we talk about that, but I don't see it in this in these pictures. I believe we're exploiting a larger fraction of the bandwidth, right. Not full,
okay.
Because there's some irregularity in the application, and we cannot perfectly stream data. Yeah, full bandwidth comes when you actually exploit the streaming bandwidth, right?
How much data is generated?
Yeah, so in this case, we're assuming that you load the data from the generator into the memory first. Yeah, we're not directly processing in the sensor here. I believe, of course, if you really want to optimize things, you need to process near the sensor. So we're not doing that yet. But to answer your question, there are some works that analyze how much data is being generated. It's large. We have, let me see actually if we're going to test the system. It's good to test it early than later, I think. So I'm going to stop sharing. See if we can do that. So we had another paper. So this was presented just at Micro. So you're looking at very, let's say, cutting edge research. If I can find my Zoom, I'm going to show you also. Okay, I'm going to skip these. This was a paper on actually in-memory analytics for genome analysis. And if you're interested, you can look at more, but I want to look at a particular slide over here. Yeah. So for example, in one human data set, one single, you can see that this is the amount of data that's generated from raw signals when you do the sequencing. And then you need to analyze it, call the bases, convert these raw signals. These are raw current signals. So in a nanopore sequencer, what happens is you pass the DNA through a nanoscale hole. And while the DNA passes through that nanoscale hole, you make current measurements. And different current measurements correspond to different bases, ACTG. And these are the current measurements. These are raw signal data. That's a large amount just for a single human genome. Now, if you convert it to ACTGs, that goes down to 546 gigabytes, as you can see, because you're compressing it, right, in a sense. And then you can eliminate some bad stuff that you don't need later on. That reduces the amount of data a little bit. And eventually, the data that you really need is 1/10 of the amount of data that you generated. This is just to show that data overall, in the end, data reduces. But if you can somehow figure out how to process it right there, as opposed to moving between different machines. Today, what happens is these raw signals are generated by the sequencing device, and they have to go out. So some other device does the base calling, and usually some other device does the analysis after that. So you're moving a lot of data across devices, basically. So our goal in this work was to actually put them all together as much as possible. So I took some time to answer your question, but hopefully it's interesting. Yes.
Is this a workload with sort of a streaming behavior where you're, suppose you could actually do this on the data collection device? Would the data collection device need to be able to hold all 4 terabytes of raw data?
Not necessarily, exactly. Yeah, so it's you can stream through it. Yeah, and we discussed some of that in the paper actually, if you're interested. Yeah, I didn't intend to cover this paper, but your question triggered it. And this was published at Micro just a few days ago. Okay, let me stop sharing this one. Go back to the other one. That's the beauty of a tutorial where we have time to discuss. Okay, I shared the wrong one. I don't know what's going on. Okay, now it's correct. Okay, so there's more on genome analysis, as I said. I don't intend to cover it, but we're designing specific accelerators for approximate string matching. A lot of these require high bandwidth memory also. There's high bandwidth access to a lot of data because there's a lot of data. And I'm going to talk about this later on, but data is so big that sometimes it doesn't fit into memory. So we look a lot into storage as well. And I think we really need to have the ability to process data all over our systems: sensors, storage, memory, caches, even register files. If you think about register files today, right, there's still data storage units. You cannot process data. You need to move data from the register file to the compute unit. There's still some distance, basically, dichotomy between memory and compute. Okay, we're going to get back to that. And I think some of the analyses are becoming more complicated. This is an example of what I said earlier, right? We want to do increasingly sophisticated things on the data. So this is happening in genome sequencing, and this is a paper that looks at graph genome. So what people have figured out in genome sequencing is it's not enough to represent, for example, a species using a single linear reference genome. You could average out, for example, which genes, which bases are where in different humans. But that doesn't work, right? Different humans are different. For example, people who live in Africa are different from people who live in Asia and also America. So people have figured out that they want to actually encode the genome as not a linear sequence, but as a graph. And this basically introduces now hops between different parts of the genome. And now you need to actually analyze the genome as a graph. And this makes it a lot harder. It actually adds irregularity to the system as well. I think this is very fascinating, actually. But the accelerator also needs to be different, essentially. Okay, so I spent more time than I expected over here, but clearly the future is going to be even more embedded. We'll have these embedded devices. We'll also have these huge devices that I showed you earlier, but we need to be able to process the data well. If you're interested in more, this is actually an old talk. We have a new version of this talk, but you can find it online probably. Or maybe some future tutorial I'll cover this. And we have a lot of lectures on genome analysis as well. So I think these are applications that are interesting. Some people were dreaming of these applications. Some people always say, why do we need better processors, right? I think my answer to that is people are good dreamers. They will dream and applications will come. We will always need better processors, basically. And this has been proven correct, I think, over decades and decades. Okay, so now let's pull back a little bit. These were applications. So these applications are clearly overwhelming our machines. I'm going to give you exact numbers a little bit more later on. But our storage and memory capability is being overwhelmed. Communication capability is overwhelmed, and computation capability in the end is overwhelmed. And also, this is the fact that we're dealing with so much data is affecting the robustness, energy, performance, and the cost of our systems. Now, if you go back to fundamentals, we do need these 3 different components: computation, communication, and storage in our systems. And if you look at the history of computing, 70, 80 years, at least electronic computing, we've optimized the computing unit heavily. We've kind of ignored the rest. Of course, that's an exaggeration, but in the grand scheme of things, that's true. So let's take a look at a single node. This is my cartoonish picture. I drew this in 2008, actually, when I wrote the grant proposal to NSF in the US. I was talking about multi-core systems, quality of service, etc. But basically, if you look at this picture over here, the computation units are only a very small part. These are the cores over here. Everything else is dedicated to data movement and storage, caches, interconnects, other caches, other interconnects, memory controllers, other interconnects, other caches, let's say, other interconnects, storage. And if you do the calculation, this single node, more than 95% of the real estate of a single node is dedicated to data movement and storage. Yet we call this a computing device, right? I think this immediately should tell us to rethink maybe what we're doing. Sorry, I don't know what happened. I didn't even touch. Okay, even then, the system is still bounded by memory. So this should really raise red flags right now, I think. We're dedicating almost all our resource in our system to memory and data, yet we're still bounded by memory. Maybe we're doing something fundamentally wrong. And that's going to be my argument throughout this tutorial. Feel free to argue back, but we don't have to agree, of course. But I strongly believe that we're doing something fundamentally wrong in the design of our systems. That's why we're having this trouble today. And if you don't believe me, these are real pictures. This is AMD's recent flagship processor. That green area over here is dedicated to L2 and L3 caches. It's not even covering L1 caches, for example. It's not covering the memory controllers. If you look at all of this, this is global memory interconnect, for example. Nothing related to computation. So, and they're adding even more caches. This is AMD's die stacked cache, another die for cache, basically. Some rumors on the internet say that you get 15% performance benefit on some important gaming workloads with this additional 64 megabyte cache. Is that good enough? I know. Is it worth the area cost that you're adding to the entire system? Is it worth the sustainability cost, etc.? It's good to think about these, I think. Okay, this is not to pick on AMD. This is IBM and their flagship processor. You can see again, the green part is pretty big. And you can see the areas around here. This is memory signaling. More memory, PCIe Gen 5 signaling. So a lot of interconnect, data communication and storage, basically. These chips are not computing chips. They're really data communication and storage chips, even though they're the computing chips, right? They're called the computing chips. Okay, this is one of my favorites, Apple M1 Ultra. I think of this chiplet design as a lot of SRAM, basically. And there's a lot of DRAM over here, and there's a darkness, which is the storage. So now I think hopefully the point is more clear. I don't even include the sensor over here. We're going to include them later on. So basically, our systems are bottlenecked by memory. Let's take a look at this bottleneck a little bit, and then we're going to see more. So we analyze these applications together with Google over the course of 1.5 years, and we published this paper in 2018. And we show that in these applications, more than 60% of the total system energy is spent just on data movement, just moving data across the memory hierarchy. And these are not the worst case. 60 actually is relatively low. There are some applications where more than 99% of the energy is spent on data movement. And some of these happen to be actually very intensive neural networks. We didn't publish this, but other people have published this. So it's good to think about this. Feel free to ask questions. We can go into more detail. I intend to cover this a little bit more later, but I'm still giving an overview. So I think maybe we need to rethink our systems and see what we're doing with our system. So I'm going to give you a broad overview of what we're thinking of how an intelligent architecture should be. I think we need to handle data well. So the question is, of course, what does it mean to handle data well? Because that will determine how we design our systems. I believe we need to take 3 steps, let's say, at least 3 steps. We need to ensure data doesn't overwhelm the components. How do you do that? I think we need intelligent algorithms, clearly, architectures, and system designs. I think this requires us to re-examine the entire stack, algorithms, architectures, and devices, and potentially co-design them together when it makes sense. Right? This is going to be the subject of this talk, basically. I think this is the core of memory-centric computing, basically. How do you redesign your system so that the data doesn't overwhelm your components and the system? But I think there are 2 other things that are synergistic with this that are also important. I don't intend to cover this in detail, but I think these are quite interesting as well. The second part is how do we take advantage of, we have a lot of data flowing through the system, right? A lot of workloads, they're generating data, they're generating metadata. Can we do better basically in the design of our controllers, for example, or policies? Today, for example, when we design controllers or policies, especially in hardware, but also in most parts of the software, these policies are very heuristic based. Some human sits and designs a policy, says, okay, this is a good policy based on everything I compare it to, let's say, yeah. And then basically they declare victory, kind of, right? But this is essentially, this is human design policy. But humans do not necessarily anticipate everything that's going on dynamically, right? If something changes in the system, workload changes, that policy may not work well. And we see in many cases that that policy doesn't work well. So for example, the memory controller in this system over here is designed by a human. It makes very simple heuristic-based decisions that doesn't consider many characteristics of the workload. It just looks at, for example, is the row buffer open in the DRAM bank? If it's open, I'm going to schedule the request that is going to hit the row buffer first, unless I delayed some other request by more than 10,000 cycles or something like that. I just gave you a very strong, close approximation to the policy that exists in many processors. So now imagine, is this really the best policy that we can have for a given workload? I would argue that not, because it doesn't even consider what is a critical request, for example, to serve for that workload, right? So I think we need to think about more learning or data-driven policies, putting more machine learning-based policies inside our systems, hardware and software. And there's a lot of work that's going on in this area. I'm happy to talk about, but we don't have time, unfortunately. And I think this is synergistic with memory-centric computing, because a lot of these policies need to be embedded near memory, in my opinion, so that you can, for example, filter the data out or schedule the request well. As a result, there's a lot of synergy. The third one is also related. The third one is today, basically, we should understand and exploit properties of different data to improve the algorithms and architectures in different metrics. So if you look at data, data has lots of properties. Right? It has clearly performance properties, energy properties, potentially, privacy properties, security properties, approximability properties, error tolerance properties, compressibility properties. So basically, you can keep adding different things. And if you think about how much of those properties get exposed to the underlying system, either software or hardware, that makes decisions on the data, essentially almost none. I mean, there's work clearly in compilers to express, for example, things like reuse distance. That helps, I think. But that's just a performance property, right? There are other properties of the data. So there are limited things that we are doing, but maybe we should be thinking more broadly and expressing a lot of the properties of the data exposing to the system. I'll give you an example from the memory controllers. For example, today, memory controllers, again, when they try to schedule between two requests, they don't consider any of these properties, right? They basically say, oh, row buffer is open, so I'm going to prioritize this request. Clearly, it's not data aware in its policy. But a data aware policy may say, oh, this request that I'm scheduling together with this request, one of those requests is very, let's say, security critical. So I should not leak any information. So I should really isolate it somewhere. So it can take a different action if it knew that that request was security critical, right? So yeah, that's one example. Like, of course, we don't know exactly how to do that yet, but I think if we think about exposing those properties of data to the underlying architecture, we can come up with a much better system again. And again, this is synergistic with memory-centric computing, because a lot of these things need to be implemented near memory, in my opinion. Okay, so I think basically we need to move from processor-centric systems to more data-centric systems. We need to move from systems that are where designers are dictating the decisions to more data-driven decision-making systems. And we need to move from systems that are making component-based myopic decisions to systems that are making decisions based on the characteristics of the data that they're dealing with. And again, I think these are all three major directions, but we're going to focus on the first one. But if you look at these directions, they all require, at least in the best implementations potentially, thinking across the stack. We all need to consider what's happening across all the way from algorithms to devices. But I believe we can get there step by step. From the memory-centric, the first perspective, I'm going to give you some examples. So this is a paper. It's a very short paper, actually, that covers what I just talked about. If you're interested, it's a position paper that elaborates a little bit more with some examples. Any questions? Okay, let's jump into the data-centric, memory-centric architectures part. If you jump into it, there's more to do over here also. So this, if I have to list the properties of a data-centric or memory-centric architecture, these are four that I would come up with. Maybe you guys can come up with some others, but I think first we need to be able to process data where it resides. We're going to talk a lot about that. But also, I think we're having some trouble with our memory system designs. We're building hierarchies to get low latency and maybe low energy. I'm not sure about the low energy part, frankly, but low latency for sure. But maybe we should really rethink how we design the memory system so that we minimize the latency and energy at the same time. We're not fully optimizing for those, in my opinion. So there's opportunity here. I'm not going to talk about that. Low-cost data storage and processing is important. Clearly, we have huge amounts of data. So how do we minimize the cost of it? I think there are a lot of things that we can do, minimize the waste, for example. Again, I'm not going to talk about that. And intelligent data management. I'm going to mention this a little bit to motivate processing near or in memory. This is really annoying. Sorry. I have to restart my computer probably, but probably it's not a good idea to do that now. Maybe during the break. Okay, so let's jump into the first one. But there are research topics clearly in all of these three. So the first one I call processing data where it makes sense. Today we have no choice. We have to move the data to compute units, either in the CPU, GPU, FPGA, your favorite accelerator. But you have to move the data to the compute units inside those, to a very small fraction of the die, basically. Why not enable all of the other parts of the system to be able to operate on the data? That's what it makes sense means, I think. And then somebody needs to, of course, decide where should you process the data, right? Sometimes the CPU is the right place to process the data because you have very good locality, or you construct the system so that you gather everything there and you amortize the cost of the data movements there, right? So, but today we have no option. We have to do that basically, and nothing else we can do. So, and clearly there are a lot of places, even in a simple chip, right? It's not even a distributed system, simple chip over here. And I think of sensors also as a place to process data. So if you think about this, it's actually not a new idea. These are some of the oldest papers that I could find. If you find some older papers, please let me know. I'm happy to add them to the list over here before these. But you can see that people have been thinking about this since 1960s. Right? It's a beautiful paper talking about processing in memory. Another beautiful paper talking about processing in memory. In fact, I think there are very good arguments there. If these arguments were followed, maybe at that time, maybe we would be in a different state today. But there's a good reason why people didn't follow those arguments also. So history is a little bit different. But we can talk about that separately. Okay, so what's new today, basically? Basically, clearly people have proposed this, but maybe because it didn't happen, we didn't really do a really thorough study of our entire systems with this perspective. But what's new today? Why should we re-examine the system today? I think there are two major reasons, and we're kind of squeezed in the middle because of these two major reasons. One is we're having huge problems with memory technology. That was not true at any time in the past. So DRAM, for example, we're going to talk about, was invented in 1965 by Bob Denard, almost 60 years ago. It's never had as much problems as it's having today. So main memory is having a lot of problems. Storage is also having problems, let's say, even though it's improved over time. So basically, memory technology scaling is not going well. And many of the, for example, there's a RowHammer problem that I will briefly talk about, but not go into detail into. And many of these technology scaling issues demand intelligence in memory. So you need to have some smartness in the memory controller so that you don't run into errors, for example, in memory. You can correct the errors or you can avoid the errors. So I think that's kind of pushing us to be intelligent on the memory side. You can think of this as limited amount of compute to protect the memory, right? That's how I think of it, actually. And clearly that now opens up, if you're protecting the memory with limited amount of compute, why not do some other compute over there? But maybe, I think the second one is perhaps even bigger. You have a huge demand from applications and systems. Clearly data access is a huge bottleneck. And energy and power. Almost all our systems are energy and power limited. And data movement energy dominates computation energy. And we're going to look at those, quantify those. And today, I think more than any other time in human history, we want to optimize for performance, energy, and sustainability increasingly. And we don't want to have a trade-off. We don't want to increase performance at the expense of energy, right? We really want to increase both performance, both increase performance and reduce energy, and somehow fix the sustainability problem. So I think we can actually improve all metrics by minimizing data movements. That's good for performance, good for energy, and I believe good for sustainability also, although I don't have a metric to really quantify that. I think energy is a good correlator potentially. So today, basically, our designs are squeezed in the middle. Maybe, in my opinion, we have nowhere else to go but have some intelligence to the memory side. Yes. I think that I use this term very laxly, let's say, in this particular case. I think of it as basically, I think of it as, can you really sustain, let's say, the future of life in the world? And that relates to clearly energy. If we waste a lot of energy, that has impact on our energy generation sources, right? And in general, waste. So I don't have a good metric, as I said, but are we doing, let's say, the right thing to minimize the waste and maximize, let's say, cleanliness in the world? I don't know, does that make sense?
Yeah, I guess it's like mental loss in the chest.
So
Yeah,
I
sure.
look at that as the useful lifetime of the system.
Yeah.
Right? Because if you make a system that has high performance controller, then you must have to throw away next year. That's not sustainable.
Yeah, you can think of it that way. Yeah, I think that's part of the sustainability equation. When does the system get thrown away? How much like carbon footprint it has when it gets thrown away? I agree. Yeah. Yeah. Okay. So let me give you before we go into a little bit more into these two aspects and motivate a little bit more. Let me give you the processing and memory landscape today. So this is circa 2011. People were putting 3D stacked memories. Basically, this is a logic layer underneath memory layers, and there are some technologies that can connect the logic die to the memory dies through silicon vias. Basically, you can have a logic layer underneath memory layers that can have high bandwidth, low energy access to large amounts of memory. So clearly, this can enable processing near the memory, right? And that's people are high bandwidth memory is an example of this. And people have been experimenting with doing processing near the row buffer, Micron as automata processor. I'm not going to go into a lot of detail in this one. It still exists, but maybe they're not developing it. But if you were sitting through this tutorial a few years ago, you wouldn't have seen this one, for example. This is the UpMem company in France. They basically built DRAM chips, which have general purpose processors next to each bank. And we're going to talk about that later on. So this is basically happening. And in my opinion, it's motivated by what I just discussed earlier in the earlier slide. Samsung have introduced machine learning inference accelerators inside the DRAM chip. We're going to talk about that. Hynix introduced something very similar. These are very conservative DRAM companies, and they're introducing compute units inside their DRAM chips. You can think of it that way, right? These companies don't normally want to do anything, let's say, inside the DRAM chip other than increase the density. Samsung and Facebook together designed these modules where they can do, again, processing or recommendation inference inside that chip over there, AXDM, they call it. And Alibaba also has introduced a DRAM chip that they designed to speed up recommendation inference. So you can see that these are motivated by real applications, UpMem being the most general purpose one. So we're going to talk about this. I think, and there are many other experimental chips and startups that are not in this picture. Basically, there are people in academia designing chips, but also some startups that do not talk as much about what they're doing, but they're also designing DRAM-based or RAM-based or flash-based accelerators. Let's cover this technology aspect first. I think technology aspect is also important because if there is no technology aspect, maybe DRAM manufacturers would be also less motivated to do some changes, right? But basically, we're having a lot of problems with DRAM technology scaling today. As a result, the industry is open to new memory architectures. They want to put controllers close to DRAM. I'm not going to cover this a lot since we don't have time, but we can go into detail if people are interested in this. I don't want to make this into a technology scaling kind of talk. But this is not a new thing, let's say. This is a paper that we were invited to write in 2013, International Memory Workshop. And we argued that basically technology scaling issues are getting worse. They're going to get even worse. Memory is going to have a lot of reliability problems, and these are going to be exposed to the system. And we need to take a system level approach to fix this. So as opposed to telling the DRAM manufacturers, it's your problem, we should really take an overall stack approach and fix the problem in the system level. In particular, the memory controller, for example, having an intelligent memory controller that can identify the errors in memory and fixes them before they get propagated into the system is a good solution direction. I'm going to give you some examples. And we collected a lot of data, actually. This paper was clearly written before we published this data, for example. This is data that we collected together with Facebook. This is data from all of their data centers. Lots of memory, lots of machines. They didn't allow us to put how much memory, how many machines, because they were scared that that would affect their stock price, because there's a lot of machines, actually. It's amazing. But basically, this is a correlational study on production data centers. You run production data center workloads, figure out how many errors you get. And these errors, the error or server failure rate or error rate, correlates with the density of the DRAM chip, memory chip employed in the server. And it's a strong correlation. If you really want to understand these metrics, you need to read the paper, because you need to do a lot of normalization. Because clearly these are different machines, right? The same machine doesn't have 1 GB, 2 GB, and 4 GB chips or gigabit density chips. So why are these chips more vulnerable? Because the cells that store the data are smaller and closer to each other. So they're much denser. As a result, there's a lot of noise and vulnerability, reliability issues. So you get more errors fundamentally in those cells. And yeah, basically you're cramming more cells into the same square millimeter. And if you're interested, you can read the paper that I mentioned over here. We did a lot of other studies also to understand some of these issues. This is our infrastructure. It's an FPGA-based infrastructure to test DRAM. And we wanted to build this infrastructure so that you can actually test DRAM and understand what's going on really. Because with a large-scale study like this, you cannot control things, right? Because this is running in a data center, and you cannot change the workload. You cannot change the system. You're just observing what's going on and plotting this data. But we would like to be able to change the, for example, the parameters in the memory controller, change the latencies and different things, change the refresh rate and understand what's going on. And we built a lot of infrastructure that I'm not going to bore you with. If you're interested, this is the paper that's open source this infrastructure in 2017. And people have been actually using this infrastructure to do very interesting studies. There was a paper at Micro this year, a few days ago, that shows that used our infrastructure to show that in real DRAM chips, you can store some fractional values, for example. If you can actually take advantage of that, it could be very useful, but maybe that's for further research. So while we were doing these studies, we also, together with Intel, we also found out that you can predictably induce errors in most DRAM memory chips. How many people know about the RowHammer phenomenon here? Okay, not everyone. So maybe I'll briefly talk about that. So this is known as the RowHammer phenomenon now. I was going to just show this picture and move on, but maybe I'll talk about it a little bit. So basically, clearly this should not happen, right? If you read something like this, this should not happen, right? You should not be inducing any errors in your memory chips, let alone predictably. So the problem is cells are too close to each other and too small. As a result, what you're doing in one cell is affecting the value in another cell. This is called disturbance in memory. And in particular, RowHammer is a read disturbance phenomenon. Whenever you're reading one row, you're disturbing the values in another row. So let me give you a high-level example of this. So if you want to read this row in DRAM, you need to apply high voltage to that row. This is called an activate in DRAM. That's good. And then you can do a read. But we're not going to do a read in this particular case. Let's close this row. We apply low voltage to that row. This is called a pre-charge in DRAM. You don't need to worry about the DRAM jargon, let's say. Apply high voltage, low voltage. That's good enough. So if you keep doing this repeatedly, high voltage, low voltage, high voltage, low voltage, high voltage, low voltage, activate, pre-charge, activate, pre-charge, activate, pre-charge, it turns out physically adjacent cells and physically adjacent rows get corrupt. So they lose their data. And this is a charge loss phenomenon. Basically, every time you do an activate pre-charge, each these vulnerable cells lose a little bit of charge. And if you keep doing this enough times, within a refresh interval before the cells get refreshed, it turns out some cells get depleted of their charge. As a result, you corrupted the data. So clearly, this should not be happening. Well, we call this the hammer row and we call this the victim row. Why? Well, it should not be happening because this is not how memory should operate, guys. You're not even writing to memory. You're not even reading data out of the array, actually, in this particular case, but you're disturbing the data. Importantly, these victim rows may belong to the same process or the operating system or some other process. So you could be correcting completely someone else's data. Okay, and more than 80% of the chips that we tested at the time were vulnerable to this. And earlier chips were not vulnerable to this because the number of activates you need to do to induce a bit flip, induce corruption, data corruption, was too much, too long, too many activates basically to fit into a refresh interval. As the cells become smaller and closer to each other, the number of activates you need to do to induce a bit flip reduces. So for example, when we did the testing in 2012 or so, the number of activates you need to do to induce a bit flip was 139,000. Today, that number is close to 7,000. So it's getting worse and worse. So clearly, this is a hardware failure mechanism that should not be happening. It's caused a reliability problem and safety problem, but also a system security vulnerability. I'm not going to talk about this aspect of it, but as a result, people are writing articles like this. It's actually a nice article. It says, forget software, hackers are now exploiting physics. Basically, using this bit flip, someone can design an attack, and people have designed many attacks. One attack is to take over the system and become root. What one can do is you can actually induce this bit flip carefully in the page table entry of a process, and this page table entry can point to your own page table. And if you flip the right bits in your page table entry that points to your own page table, you can gain write access to your own page table. And if you gain write access to your own page table as a user level process, well, you're not supposed to do that, right? That breaks all memory isolation, clearly. So basically, the fact that there is no physical isolation between the DRAM cells leads to a fundamental problem with isolation, which is required so that you can actually be secure, right? Okay, so I'm not going to talk about that. Okay, but if you're interested, we have a lot of lectures on it. And this is, I think, in my opinion, its own tutorial, frankly. Well, it was a tutorial here in the International Memory Workshop recently, but that's a shorter tutorial. It was just 1 hour. Their notion of a tutorial is a little bit different than the notion of a tutorial here. And if you really don't have time for 50 minutes, we cover also in 20 minutes what happened in RowHammer. So this RowHammer is actually getting worse. It's really a technology scaling problem. It's not going to be solved that easily. We'll see what happens. And as a result, so let me tell you what I mean by putting intelligence. As a result, both memory controller manufacturers and DRAM manufacturers are putting intelligence to their memory. Normally, they don't want to do anything to the memory, as I said, because it cuts into their costs. Now, all major DRAM manufacturers have put in RowHammer defenses in their DRAM chips. Now, these are not perfectly secure. That's a totally different issue. But they're going to get even more and more higher cost. They're going to get even more intelligent, basically. And if you're interested, you can read the papers that we wrote. And if you want to do research in RowHammer, actually, I encourage that. And this covers a lot of the space until 2019. And this is essentially a survey article that covers what's going on in RowHammer until 2019, all the way from devices to algorithms and system security, for example. But what has happened since 2019 is actually also interesting. Okay, so that was one scaling issue, like RowHammer. Retention errors are another scaling issue that I'm not going to talk about. Those are quite interesting. Let's take a look at another scaling issue. So if one memory technology doesn't scale very well, like DRAM, why not have other memory technologies next to it? It could be some other types of DRAM. It doesn't need to be phase change memory, but it could be phase change memory. Basically, the key idea here is to have heterogeneous memories. And different memories have different greens, good characteristics, and different reds, bad characteristics. And the idea is to design the system, both the hardware and the software, to manage the data allocation and movements dynamically, so that you can exercise the greens of each technology as much as possible, while avoiding the reds of each technology as much as possible. I think that's a beautiful idea, clearly, but this requires, again, intelligence in the memory system, right? Your memory controller cannot be a dumb memory controller that just controls things, right? It needs to identify what data needs to go where, potentially cooperatively with your software stack, right? So this is another technology scaling trend that requires intelligence. And this is already happening, I think. So our control is actually getting into more and more intelligent. So I believe these sort of technology issues require more intelligence, intelligent controllers. So this is an example RowHammer solution that is even more intelligent than what's implemented in the field. If you're interested, you can take a look at these things. And industry is also arguing for this, actually. This is a forward-looking paper from Samsung and Intel. These are two companies that don't normally talk to each other without lawyers. But they actually wrote, this is the only paper that I know of that was written by Samsung and Intel together, co-authored. And in this case, There's no author that went from Samsung and Intel. That's why it doesn't happen that because of that. They actually collaborated to write this paper. And they basically said what I've been saying basically so far in this right now. DRAM process scaling is difficult. Let's have intelligent controllers to fix the problem. So they talk about intelligent controllers doing error correction, for example, in this work. I'd recommend this paper also. This is only 4 pages, by the way. Their presentation is very good too. So there are many, many intelligent control examples that I can give you. This is one of our more recent works done by one of my PhD students which basically uses the error correcting codes inside existing memory chips to identify uncorrectable errors. You need some intelligence in the memory controller to be able to do things like this, for example. So another example of intelligent control is NAND flash memory. Flash memory SSDs clearly have been a very successful memory technology. I think this is actually enabled by flash memory, in my opinion. I wouldn't be taking so many pictures without that flash memory inside here, right? And many, many more things, not just pictures. But this requires an intelligent memory controller because there are so many errors. And I think DRAM main memories are also going to be very similar to flash memory. This is a paper that we wrote some number of years ago that talk about the mechanisms that are employed in flash memory-based solid-state drives to minimize the errors, basically. How can we get rid of the errors? So if you look at flash technology, it is scaled to a point that when you manufacture a flash chip, it doesn't work. What do I mean? There are too many errors on that chip. You really need to have an intelligent controller to fix those errors. Dynamic. So controllers actually employ many, many techniques for that purpose. Any questions? This is another tutorial by itself, by the way. I think flash memory is very fascinating. Okay, let me give you, before we move on to the system level aspect, I'll mention one more thing. What about other technologies? Like you can say, okay, these technologies are not scaling. Is there another technology that's going to scale and do better? Maybe we're going to replace, and what I'm talking about is useless. Right? Unfortunately, we haven't figured it out yet. Phase change memory, for example, is a potential technology that's scalable, but even it has a lot of errors. So Intel Optane, for example, unfortunately, Intel canceled it recently, according to what they say. Hopefully, some other people will pick it up. This doesn't mean that research is tough, but basically, to be able to make this work, Intel, for example, put intelligent controllers in there to overcome the errors, endurance effects, for example. And this is a paper that we wrote, which also are for intelligent controllers over there, but I'm not going to talk about that. Okay, so this was a long-winded talk about how technology scaling is causing issues in the memory side and we need intelligent controllers to overcome those issues. Now, let me jump into the system and application side and give you some data. And then we're going to talk about some methods for in-memory and in-storage computation. So systems and application side, again, as I said, arguably this is even worse. We're having a lot of problems with data. Now let's take a look at these. I think this is the sustainability aspect that I was thinking of. Do we want a world that looks like this? Or do we want a world that looks like this? Maybe 1940s Pittsburgh. I used to live in Pittsburgh. I like Pittsburgh, but I don't like this Pittsburgh. I think we don't want, I mean, clearly people who want to live well don't want this. But I don't think we want to give up high performance. We don't want to be living in a world like this where problems still exist, right? We really want the best of both worlds. And I think that requires us to be high performance, energy efficient, sustainable, all at the same time. As I said earlier, we don't want a trade-off between performance and energy. So far, we've been making that trade-off, right? We're increasing performance by 3%. It increased energy by 1%. Maybe that's a good trade-off. In fact, sometimes people are arguing 1% increase in performance is worth 3% increase in energy. I don't buy that anymore. I think that's not a good way of improving systems. So let's take a look at the problem. Clearly, we've discussed this. Data access is a major performance energy bottleneck. And our current design principles cause great energy waste because we're moving data from the processor and memory at the very least, from the memory to the processor at the very least. And we know that this is causing performance problems. I put this in parentheses because we try very hard to eliminate the performance loss, right? What do? We complicate our systems. We add out-of-order execution, again, both in hardware and software levels. Out-of-order execution, many, many levels of caching, many, many levels of multi-threading, a huge memory hierarchy. And this is compounding the energy waste. So we're in this vicious cycle. We have energy waste because fundamentally we're moving data, and this complexity that we're adding is wasting energy. And sometimes actually this complexity that we're adding is not improving performance also. So it's there just as a baggage. It's good to think about this. So for example, there are some workloads that are reasonably random access, and most of your techniques are useless, I would argue. Maybe not all the time, but at least some of the time. But sometimes it's all the time, right? Run a random access workload, GUPS, for example, giga updates per second, very simple workload on your system, and see how your cache hierarchy works. It's terrible. So this is really compounding the energies. In fact, we had a paper at this micro, which is interesting. It actually won one of the best paper awards at micro. But basically, the basic idea was to predict when you should bypass the cache hierarchy. Because there are many loads that are going to miss in your cache hierarchy. And it makes no sense to go through your cache hierarchy because it takes so much latency. So why don't you bypass the cache hierarchy, so fetch the data so that you can get the data much faster? So it's not only wasting energy, it's also making our performance worse in those workloads when they don't work right. If you look at the cache hierarchies of today, it takes about 70, 80, 100 cycles to figure out you're going to miss in the on-chip cache hierarchy. And that's what our work tried to do, basically. Figure out that you're going to miss the cache hierarchy and then bypass the cache hierarchy so that you can start the memory access faster. This is within the compute-centric domain, of course. That's not, we're patching the compute-centric architecture, basically, if you think about it. Okay. So all of the complexity we're adding to our systems is not helping energy, but it's also not helping performance sometimes. And I think whenever you have a vicious cycle, it's always good to identify what the problem is. I think the problem is basically this. We're processing data far away from the data. And I've shown you these pictures. All data is processed in the processor at great system cost. Now let me give you some data. Well, again, let's start historically. How many people know about Dick Seitz here? I think Jose knows, but he's too nice to raise his hand. So Dick Seitz was the chief architect of alpha processors in 1990s. He led a team that designed the flagship processor of its time. Alpha processors were competing with Intel, if you don't know about that. And they were actually quite good. And his team designed a flagship alpha processor at the time. After that, he wrote a one-page article. I would recommend people to read that article. It's entitled this. I copied part of the article over here, the beginning of the article. He basically says it's the memory stupid. Basically, he says that we designed this processor to finish 4 instructions every 1 clock cycle. So 4 instructions per cycle. That's the IPC of the processor, right? Maximum. It's capable of doing that. But unfortunately, in this workload that we thought we designed this processor for, which is a database type of workload, it's finishing 1 instruction every 4.5 cycles. So it's operating at 1/18 of its peak bandwidth, right? And he basically says, why it's waiting for memory. And he ends the article, sorry, not with a blank screen, but with saying that I expect that over the coming decade, memory subsystem design will be the only important design issue for microprocessors. And clearly, I agree with this. And I think this is mostly true, but unfortunately, we're stuck in this compute-centric paradigm. We're going to talk about adoption issues later on also. Okay, so this is data from my own PhD thesis. So I'm proud of this picture over here. This is my first paper that I wrote during my PhD. Together with Intel, we analyzed all of their memory-bound workloads in their systems that they use to design their processors with. And basically, we found out that more than 50% of the time, the processor is waiting for cache misses to come back from memory. These are flagship processors of their times, if you can think about that way. And this is my first paper. Okay, if you don't believe me or Dick Seitz, since everybody believes Google, I'll present some data from Google. They basically show the same thing. Let me put it that way. In fact, maybe more convincingly, because they have these real workloads. Well, other workloads were also real, but these may feel more real since it's Gmail, right? But basically, these are all of their data center workloads according to them. And they basically say, most of the time, the processor is waiting for memory. The backend bound part is really waiting for memory. The green part is finishing instructions, not a lot of the time, as you can see. And this is a flagship Intel processor of its time. Basically. It's supposed to be doing very good computation and very good performance. And they have very good analysis. This is also another paper that I would recommend. It's written in 2015, but I think it's still, a lot of the insights are still applicable. The problem is not getting better, basically. Okay, so I think I've already harped this. I'm not going to cover this slide, but maybe I will mention that we have a grossly imbalanced system. Everything has to go through the processor so that we can process it. and processor becomes overly complex and bloated as a result of that. And it's not good for energy efficiency, performance, or complexity. And that's why we have this picture that I showed you earlier, right? Okay, so let me give you the energy perspective. We didn't talk a lot about energy so far, except for the 62% number that I threw at you. Where is that 62% number coming from? It's coming from the relative cost of computation versus data moment in terms of energy. So this is old data, doesn't matter. This is from 2015. Bill Daly's presentation at High Peak. Bill Daly is the chief scientist of NVIDIA and professor at Stanford. But basically, a 64-bit double precision floating point operation is 20 picojoules. This is a complicated operation, not a simple one. And memory access, DRAM access, 16 nanojoules. That's 800x difference. And you can argue, okay, you can optimize the DRAM access. Yes, you could, no question about that. But you cannot take it below 100x basically. So there's a disparity of 2 to 3 orders of magnitude energy in terms of computation or between computation and communication. Now it's good to think. I have 2 points to make over here actually. This was not always the case. First of all, if you go back 70 years ago, we don't know exact numbers. Of course, we don't have the exact numbers right now. They were not published, etc. But based on some scaling that you do, the cost of a complex arithmetic operation was about 2 orders of magnitude more in terms of energy compared to a memory access. What has happened over the course of 70, 80 years is essentially great technology scaling. Technology scaling helped the logic gates very well. It didn't help the memory or interconnect. So logic gates scaled, became better performance, smaller and lower energy, but interconnect didn't scale as well. As a result, we're 5 orders of magnitude to the other side right now. The other point over here is it's good to think about. In fact, it's good to think about how much locality you need to have to overcome this energy cost. So you assume that you have one workload, one arithmetic operation. You need 2 operands, right? You need to access 2 operands from DRAM. That's 2 times 16 nanojoules. Do the arithmetic operation, 20 picojoules, and then write back the destination, write back to DRAM. That's another 16 nanojoules. How many times do you need to reuse the operands to overcome this energy cost? And you will come with a whole lot of times. That's a lot, actually. I think Wen-Mei Hu actually has these numbers in one of his presentations. I'd recommend looking at it. It's something like 2,500 or 3,000 times or so. I didn't do the calculation with these. I don't know if he did the calculation with these numbers, but it's around the same ballpark. Okay, that was a complex arithmetic operation. Let's look at a simple arithmetic operation. Simple integer add, 32-bit. You can see the relative cost is even worse. So a DRAM access 6,400 times more energy than a simple arithmetic operation. And you can see that even multiplication is not that costly because we know how to build computation logic, basically. That's the key. You've scaled really well over there. We have not scaled well in interconnects. Okay, so there's more we can, basically there are a lot of other papers that also quantify this that I'm not going to talk about. As a result, we have numbers like this. Most of the system energy is spent on data moment, on real workloads. So, okay, I think we do not want to move data. I would argue that. Or we need to know what we're doing when we're moving data. We need to amortize the cost of data moments. But to be able to do that, I think we need to enable some options for us. Enable computation with minimal data moment, compute where it makes sense, where data is right, and make computing architectures more data-centric. Now we're going to go into mechanisms a little bit. But before we go into mechanisms, let's take a look at the overall picture. I'm going to focus on memory, but you can imagine that we can do this to the cache, we can do this to the storage, we can do this to the sensors, whatever. And I'm going to focus on this as an accelerator model. So we're not even going to push memory as a, let's say, we're going to build an operating system inside the memory and memory is going to do everything. I'm not going to talk about that at this point. We're going to talk about memory as an accelerator. So what does that mean? Processor. Memory already stores a lot of things like in-memory database, in-memory graphs, in-memory machine learning engines. And processor queries the memory, asks the memory, can you execute this function for me on this huge amounts of data or on this piece of data and return the results. And the memory returns the results. There are many questions even with this model. Right? How do you design the memory and the controllers? How do you design the processor and the communication units? How to design the software and hardware interfaces to enable this. I don't believe we have the right interfaces for this at this point. How to design the system software compilers and languages to enable this easily. Well, enable this is first, and then easily is the second. That's another question, right? And then how do you design the algorithms to fit what's going on the memory side? As we will see, memory can be designed in different ways to do the computation. And maybe even think about theoretical foundations of computing. I'm going to mention that in a little bit. But if you think about it, all of these questions span across the stack. You really need to rethink what's going on in the stack, including devices to do computation inside the memory and algorithms to fit what's going on, fit the computation inside the memory, right? And everything in between. I'll mention theoretical foundations because I think this is very interesting. This is showing how ingrained this compute-centric paradigm is in our computer science curriculum and thinking, right? If you think about the theory of computing, probably almost all of you have taken some algorithmic complexity class. And what you've done in that class is probably counted the number of operations that you do, right? Big O notation, big theta notation. It's good, it's beautiful, actually, no question about that. But is that the right thing to do? I just show you that operations don't matter in terms of energy, but we're counting operations. We don't even think about data movements, amount of data, how much data is being transferred. So all of our theory is compute-centric. So this is a great opportunity, I think, for innovation and for theory-oriented folks. Okay, so now let's go into some techniques. In this paper, we cover a lot more, actually. We don't have time to cover everything, but we keep updating this paper on archive. We recently put another version of it. So if you're interested, this is the state of the art that covers lots of stuff, including what I've talked about as well. Okay. And we also have a processing in memory course. I should probably advertise this. People are interested in attending. We live stream it. You can ask questions. You can see that there actually, I don't know how many lectures I can read, sorry, 18 lectures or so that covers, it can be a full course by itself, as you can see. And we cover some of the existing engines as well. So I would argue that we need to think differently from past approaches to be successful today. And we should focus on adoption. I'm not going to talk about adoption right now. We're going to talk about that later. But let's talk about what are the approaches to processing in memory. I broadly categorize processing in memory into two. I'm going to talk about the more forward-looking approach first, which is the using memory, unless people want me to talk about the less forward-looking approach, which is processing near memory. Processing near memory is already happening. So what is processing near memory? Let me describe that first. So you have a processor here, right? We said memory is far away. Why not put the processor closer, 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 closer? And at some point they get integrated, right? But the processor is similar to what we know and what we're used to. It could be a CPU. It could be a GPU. It could be some reconfigurable fabric. It could be some accelerator. So it's essentially logic as we're used to. You're just combining it or getting it as close as possible to memory. At some point, it's so close to the memory arrays that, but it's still there. It's distinguishable. That's near memory. And fundamentally, this is not as disruptive. It's still disruptive, as we will see. It still needs you to rethink some of the abstractions that we've developed. But it's not as disruptive because it's still computation, right? It's still some logic that we know how to program. We just need to do it in some other place, let's say. Using memory is different. You have processor memory, forget the processor. It's gone. Now it's memory. What do you do with this memory? If you ask a compute-centric guy, they will sell you nothing, right? Because it just stores data. But processing using memory says, oh, this memory, it's not just memory. All memory has some computation capability, analog computation capability. So based on the operational principles of the memory and the cells, I can compute inside this memory. So exploit the operational principles of the cells to do computation. I'm not suggesting eliminate the processor. This could be a good accelerator also. That's the idea. But this memory can be repurposed to also do computation. And I think this is why this first one is more disruptive, because you're not adding any logic. This is something we're not used to, right? And we will see how we're not used to it. You can exploit it, but you need to rethink some of your algorithms to exploit what we're going to discuss. Any questions? Is it time for a break, or not that I need a break, but 20 minutes? Okay. Okay, then we can cover some of processing using memory. Just stop me if you need a break, because I can keep hammering you. Yes, please. Yeah, I think, maybe you can ask that question later on. I believe you can solve any problem with both of the approaches, frankly. The question is a matter of efficiency. And also, I should also say this is currently a moving target, right? We don't know exactly how to do processing using memory extremely well yet. We have some idea, but this is a mostly unexplored approach in the past. This is really happening within the last, I don't know, 5-10 years at most. People have not explored this as much in the really old days. Near memory, people have explored it for, let's say, 60+ years, but maybe not to the same level of detail that we're doing right now. Okay, so let's jump into processing using memory, if this allows us to do so. Okay, so as I said, the idea here is to take advantage of the operational principles of memory to perform bulk data movement and computation. You can exploit the internal connectivity inside the memory to move data efficiently. I'm going to start with that because that's the easiest thing you can do, actually. And then you can exploit analog computation capability. And as I said, in my opinion, all memory technologies have some computation capability. They're not used today, but they do have that based on the principles of operation. I'm going to show you how to do that in DRAM. We're going to discuss how to do that in non-volatile memory. In fact, we have a paper in Micro that shows how to do that in flash memory, even more efficiently than DRAM, actually. So I think this is very fascinating. And who knows what else, right? You could do more. So let's start simple, not even talk about computation. Let's talk about data copy and initialization. And I think it's good to look at this because this shows how inefficient our systems are today. So clearly, data copy and initialization is used for many applications and primitives. Operating systems initialize pages to 0, for example. That takes a lot of time. Imagine initializing a huge database, 4 terabytes to all zeros or whatever number that you want to initialize to. In fact, this paper that I mentioned from Google that was written in this 2015 showed that only 2 function calls, memmove and memcopy, are responsible for 5% of the execution cycles across all of the Google data center workloads. I think this is fascinating to me. These are 2 function calls out of so many function calls, right? 5%, that's a lot. So how do we do in-memory copy today? Basically, if you want to copy the source page to this destination page, you have to go through the processor, at least the memory controller, through the direct memory access engine. Basically, you're wasting a lot of data movement. That's part of the data movement cost that we discussed. So why don't we enable the memory to do this internally? Copy the source page to the destination page internally. It could be done at different granularities also, but we're going to talk about page granularity for now because that's actually the most efficient you can do inside the memory. You can do smaller granularity, that becomes a little bit less efficient, but it's still more efficient than going through the processor actually, or exercising this huge bottleneck process. So this is low latency because we're going to exploit the internal connectivity in memory to do this. Low bandwidth utilization, you don't move any data to the processor. No cache pollution, but you could eliminate that actually by doing this through the direct memory access engine in the memory controller, and no unwanted data movement. So I'm going to show you a mechanism that takes this 1,000 nanoseconds, that's for 4 kilobyte page copy today, to 90 nanoseconds, and 3.6 microjoules to 0.04 microjoules. These are unoptimized. You can optimize it to even better. Let's take a look at how we can do this if the source and destination pages are in the same DRAM subarray. This is the fastest you can do in DRAM, as far as I know. The idea is called row clone. It's a very simple idea. You first activate the source row, which brings the data into the sense amplifiers called the row buffer in DRAM. These structures all exist in DRAM. And then you activate the destination row, which implicitly deactivates the source row and connects the sense amplifiers to the destination row, which means that you copy what you copied into the row buffer into the destination row. So you use the row buffer as a temporary buffer to copy data from row A to row B. You still move data, no question about that. But this is intrinsic to the operation of DRAM. Whenever you need to read a row, you have to move that row to the row buffer in DRAM anyway. That's the idea. So by doing 2 consecutive activations with negligible hardware cost, you can actually do this copy today. Yes, please.
That's almost, I mean, it's interesting, but it seems almost an unintended consequence to the design of DRAM. So if it was, like DRAM designers were more intentional about enabling this, could they make it more efficient? Like, through like a mechanism, or like if this can happen to the test that can be done, and we're also getting it free today.
So you're getting it free today because this is how DRAM operates. This is the analog operation of DRAM actually internally. You have to have the sense amplifier to amplify the data inside the DRAM cell. There could be other DRAM designs that can do this more efficiently, or you can actually add more cost to the DRAM, but that requires changes to the arrays. So certainly, I'm not claiming that this is the most efficient way, but it's the most efficient low-cost way of doing things. In fact, you can do this without changing the DRAM chips today. So when we wrote the paper in 2013, we said you need minimal changes. And later, basically, let me give you the results first, and then we're going to talk about that. So you get basically significant performance and energy improvements on a 4 kilobyte page copy. And clearly, it depends on where your data is. If your source and destination rows are in the same subarray, that's great. But if they're in different subarrays, then you have a problem. But we have solutions to that I'm not going to talk about. So you can actually reduce these bars significantly, also closer to not lower than the red bar over here, but close enough to the red bar, let's say. And that's the paper that introduced the idea. 6 years later, these folks from Princeton showed that you could actually do this in off-the-shelf DRAM chips, meaning they took the infrastructure that I showed you, the soft MC infrastructure that we built. They actually used it. They violated the DRAM timing parameters so that they could do 2 consecutive activations right after each other. And as a result, most DRAM chips that they tested were able to do row clone reliably. So this is, I think, fascinating because DRAM is clearly not designed for this. Nobody specified that DRAM is supposed to be doing this row copies, but you can do it by violating the timing parameters. This shows that the memory has the capability to do that. Now imagine if someone actually went through and designed the memory to do this more robustly, right? Okay, and later we built on these. Yes, please.
So this brings my problem with the interplay between this kind of actions in memory and the memory hierarchy. Yeah. Right? Yes. Because now the entire memory hierarchy needs to be aware of that.
Yes. So we just this paper actually discusses that a lot.
In this case, I'm visualizing something that the processor is aware of what it's telling the DRAM to do.
Exactly.
And the DRAM will do the movement for it.
Yes.
But as we make it more sophisticated, we may have a conditional that is executing the DRAM. And now the destination may be determined at runtime.
Yeah, potentially.
And then we have the problem to send back to the memory hierarchy the information of the what function.
Sure. Yeah, certainly. I think you can. We didn't do that clearly in these works, but I think it can certainly be extended to be more efficient. Like if you need these pieces of the row that you're copying, also send them to the memory hierarchy. Is that what you're envisioning?
No, the problem that I'm envisioning is that some of the content that you're changing the memory is actually
inside the caches. Yeah.
And an invalidation doesn't happen.
Sure. Yeah. Coherence needs to be done. Yes. We cover a lot of this in this work, actually. System level issues like coherence, data alignment, where should the data be? When can you do it? When can you not do it? When is it not efficient to do it? Yes, all of those need to be considered. I agree with that. In fact, coherence, we're going to talk about that. That's one of the hairy issues if you have copies of the data in the memory hierarchy or cache hierarchy. Okay, very good points. So we later extended these folks' works to actually design an end-to-end FPGA-based framework that we called PyDRAM. You can download it, actually. This is freely available to people if you want to get your hands dirty in a real FPGA-based infrastructure that can do processing using memory, especially the row clone, actually. The idea here is it can run a very simple operating system and some applications, and you can look at the effects of doing this on real applications end-to-end. It is limited in some ways. You can read the paper for more detail, but I think it's a good step in the right direction because people can now experiment with it. We not only support row clone, but also true random number generation. It turns out by violating the timing parameters, you can also generate true random numbers in DRAM. I'm going to mention that a little bit later, but I'm not going to focus a lot. But basically, memory has the capability of generating true random numbers using its analog operational properties also. You don't need a specific true random number generator. So you can call, for example, I think we call it the PyRand or something like that, processing, I don't remember. But in DRAM rand, you can call it from your application and the DRAM supplies a random number to you. And this is what it looks like. So you basically have a RISC-V processor that communicates with, the RISC-V processor executes the application and it can actually send commands to DRAM, our special memory controller. And our special memory controller executes those functions by violating the timing parameters. So rand goes there and then you get a random number from the memory controller. And you can certainly do more. So we actually did experiment with what I'm going to talk about next, and we may actually release that as well. So if people are interested, we're happy to support it also, actually. Okay, and this is one example result that we get. This is a real micro benchmarks, and you get huge speed ups actually, because there are some system level inefficiencies that you eliminate as well. Okay, so there's more that can be talked about in terms of data copying, but I'm not going to talk about that. I'm going to switch to doing actually computation. And remember that we're still thinking of memory as an accelerator, right? You have this accelerator over here. We have so many accelerators over here. Why not have an accelerator over here? You can think of this as a data copy accelerator. And I didn't talk about initialization, but initialization is a special case of data copy, right? You initialize one row to all zeros and then copy that row. Okay. Okay, so let's talk about computation. This is a bit harder, but again, it's doable. Similarly, we can support in DRAM majority, that's our primitive, and not. And majority can be broken down into AND and OR. So let's see how we do that. Again, we're going to use analog computation capability, and we're going to introduce the primitive of multiple row activation, in particular, three row activation, triple row activation. And you get significant energy and performance improvements on these primitive operations. Before I go introduced in DRAM, what I'm going to describe actually works in non-volatile memory also. There are papers that talk about that. I'm not going to talk about that right now, but we'll talk about that a little bit later. But non-volatile memory, emerging memory technologies actually introduce other potential benefits also, which I'm going to talk about after we're finished DRAM. And also they're fundamentally non-volatile. They can operate with minimal data movement because you don't destroy the data. Their structure is fundamentally different, basically, as we will see. But let's stick to DRAM. So let's take a look at what triple row activation does. Imagine 3 rows in DRAM, A, B, C. I'm showing only one cell in each row. Each row is actually 8 kilobytes, for example, depending on the DRAM chip. And you can actually do this operation across 1,000 subarrays, let's say in DRAM. So 8 million bits at a time, which is nice, clear. But let's take a look at 1 bit. So we're going to do a triple row activation, which is activate 3 rows at the same time, connect those 3 cells to the bit line. Now, if you do this in an ideal circuit, you get a majority function, bitwise majority. If 2 of these cells are charged, you get the charge state at the end over here. If 2 of these cells are discharged, you get the discharge state. And that's bitwise majority, right? And bitwise majority is a beautiful function, actually. I think Donald Knuth, in his 4th volume of his The Art of Computer Programming, talks about bitwise majority as a beautiful function and shows what you can do with it. You can express your algorithms as bitwise majority. Now, you need something else, actually, to be functionally complete, which is a NOT inversion. Okay, before I move into that, you can express bitwise majority as AND and OR. If you set C to 1, you get the AND of A and B. If you set, OR of A and B. If you set C to 0, you get the AND of A and B. Now you get AND and NOT function, bitwise. What's missing is inversion, right? But you can see that it exists already here, right? So this is, when you sense the data, this is the value, and this is its complement. So complement is actually on the other end of the sense amplifier. You just need to supply it somewhere and make use of it. And that's what we do in the paper that I'm not going to talk about. This requires a little bit more change to the DRAM circuit. But fundamentally, you can see that we're not adding any logic to these operations. These operations are happening in analog, in the operational principles of DRAM. NOT is also there. Well, NOT logic is already added because it has to be there, right, for sense amplification. But we're not adding anything extra to do the NOT. Okay. So that's the idea over here. So now we have a functionally complete system, meaning you can clearly AND and NOT is complete, OR and NOT is complete, and majority and NOT is also complete functionally. Now, if you have a functionally or Boolean complete system, all you need to do is rethink your algorithms to take advantage of it. And I believe you can actually map any algorithm. But some algorithms are actually more amenable. For example, bitmap indices in databases, they use a lot of bitwise operations across many large vectors. People actually have designed databases to maximize those bitwise operations so that they can be more efficient on GPUs. Bitweaving databases 1 from 2013. Microsoft designed this Bitfunnel web search engine. Again, very similar principles. Maximize bitwise operations. A lot of DNA sequence mapping can be maximizing bitwise operations, set operations, encryption algorithms. There's a lot, actually. And we actually did this in simulation, and I don't know what's going on, sorry. Basically, we mapped this bitweaving database that was designed in 2013. Now it's not coming back up. Sorry. that was designed in 2013 to our Mbit engine. Oh, now my computer is stopped. Maybe it's telling us that we should have a break. Yeah, but maybe it is time for a break, but I don't know what's happening. Say it again.
We have half an hour.
Oh, okay. Let me finish this if I can, but if I cannot, then that's fine. Okay. Okay, it's back. No, that was scary. Okay. So basically, we see significant performance improvements. This is end-to-end performance improvement on query execution. And I mean, I don't want to go into detail of these numbers. If we have to, then we don't have time for anything else, basically. Okay, so this is the paper that introduces Mbit, and there's a lot more here. And there are some open issues over here also. For example, how do you do error correction? And in this paper, we talk about some of those open issues. Unfortunately, error correction is not easy with these things. And that's one of the reasons why I believe that this is a little bit longer term. With near memory computing, we can do error correction because it doesn't change the model. Here we change the model, right? Everything is happening in analog. How do you do the error correction concurrently with that analog operation? There are some heavyweight methods like triple modular redundancy. You do these operations 3 times and then select what basically, but those are not very good. Even then, actually, you can improve performance with that huge wastage. Okay, let me give you how to generalize this, and then I think we can take a break. Is it really break time right now, or?
A few minutes.
Few minutes. Okay, I'll take a few minutes to generalize this because we should stop at the right boundary, let's say, so that we don't need to warm up our caches again, let's say, since we're not sitting in memory. Yeah. So we recently wanted to generalize this so that we can implement any operation easily, and also match it to the existing programming model. Now, we could argue that this is not a good thing, but I mean, it's good for adoption. Let's say if people want to adopt these things, I think it's good to integrate your mechanisms to existing programming models as much as possible. It takes some of the power out of the mechanisms potentially, but I think in this case, we see significant benefits. So basically, the idea is this. The user can specify any operation they want, and they just need to be able to express it using and or not logic. As logic gates, let's say. It could be a convolution operation, for example. It could be matrix multiplication. Pick your favorite operation. It could be a division. It could be something simpler. And we generate majority logic, majority and not logic, using something called majority inverter graphs, which was done by Nani Demicheli's group at EPFL to optimize the circuits. Actually, they were optimizing quantum circuits. We're applying it to more traditional classical circuits. But basically, you can minimize this using some transformations, computer-aided design transformations. And then, based on that, we generate a microprogram, which is essentially a sequence of DRAM commands that can execute that function. Now, it's just, this is not just sequence generation. It's actually some sort of compilation because you need to allocate some rows also. So there's some row allocation going on, similar to register allocation, etc. So basically, you create this microprogram. Now, this microprogram is specific to this function. Call that as new bulk bitwise operation. It could be convolution, bulk bitwise convolution. And it gets stored in main memory. And then when the instruction is called by the program, this instruction gets shipped to the memory controller. Memory controller executes the microprogram associated with the instruction so that it can actually complete the operation in DRAM. So this can be done in our PyDRAM architecture, for example, although we didn't do it because using these bulk bitwise operations is not easy in existing DRAM chips, although potentially some of the DRAM chips support it. Okay, so that's the idea basically. And we see significant performance, even more performance and energy improvements compared to the prior works that we have done and others have done. And I'm not going to bore you with the numbers, but you can see that on these operations, we can outperform. Some of the operations, of course, are very difficult. For example, if you want to do a 64-bit multiplication, we're doing it bit serially, right? Bit by bit, because this is bulk bitwise. It takes a lot of latency to do this. So we don't necessarily outperform just in that 64-bit multiplication, but you get a lot of parallels, bitwise parallels. So that's the good part. You can do a lot of multiplications concurrently. Latency is bad, but concurrency is very good. And of course, division is even worse, right? And we analyze those operations. So that's SimDRAM. In this micro, we wanted to, some of the operations are actually even, some of the operations that are not efficient using SimDRAM can be done using lookup tables. So we introduced the idea of using lookup tables inside the DRAM and some primitives. This requires more changes to DRAM, of course. The overheads here are actually much larger. This way you can actually do division, exponentiation, things like that much more efficiently in DRAM, because those are fundamentally converted to lookup table lookups in DRAM. I'm not going to go into this, but if you're interested, you can take a look. Okay, maybe. Yes, please. Well,
Somebody we're talking about like massive parallels. If we're talking about like how much parallels, like how much if somebody like you're doing a single instruction, how much data you can do at once.
yeah. So let's say 8 million bits at the same time in DRAM. You could potentially do it.
Okay, yeah, that's that's one.
Yeah. It depends on how many, if this is within a DRAM module. If you have 10 DRAM modules, that could be 80 million bits, right? If you're doing concurrently in all of them. Of course, this increases the power requirements of your DRAM a little bit, but nothing is free, right? There's no free lunch. If you're doing computation, you should increase your power also.
Yeah, you're gonna have to do more instructions as well. You should transit
Exactly, yeah. Okay, I think we should really take a break at this point. Oh, okay. Okay, I'm going to cover processing using memory, and then we're going to switch to the easier part, processing near memory. In using memory, we're almost done. We discussed these block bitwise operations, and then lookup table-based operations. Even though we didn't go into detail, you can imagine what they are. I think it's interesting. But you can do other things, as I briefly mentioned. For example, you can reduce the latency, violate the timing parameters, and some cells in DRAM fail consistently if you do that. And those cells that fail consistently when you violate timing parameters, activation latency, for example, happen to form a signature of the device. So it can be a physical unclonable function that is used to identify the device. So this is one interesting work that we've done, and we've shown using many DRAM chips that this is true actually. So it's actually interesting, I think. So you can build a security infrastructure on the memory side as well. And similarly, with a similar insight, it turns out when you violate the activation latency of DRAM cells, some cells fail randomly. 50% of the time they fail, 50% of the time they don't fail. So you can use this information as a true random number generator, because as far as we know, the randomness is caused by the noise in the sense amplifier, which, as far as we know, again, is a physical process that leads to true random numbers. And we analyze the randomness of this using NIST tests, etc., and they pass all the NIST tests. So I think this is also fascinating. Basically, you don't need to build random number generators. Memory is a good random number generator itself. And we also discovered that some other phenomenon in DRAM leads to true random numbers in a better way, in a higher throughput way. We call the QUAC TRNG. Basically, if you activate 4 rows concurrently, it turns out you get a true random number again. On some cells, not all cells behave this way, but some cells fail randomly. And we have why this is happening. You can think of it as 4 cells competing with each other, right? And eventually the noise in the sense amplifiers wins in terms of to determine whether you get a 1 or 0 sense. Does that sound interesting? Yeah, I think it's interesting. Maybe there are some other ways of generating randomness. Sorry. I think this is related to idleness. If I stay idle for 5 or 10 seconds, this goes blank. So maybe I should just keep pressing something. And then, of course, how do you integrate these things end to end is an important question. Here we look at how to integrate it into the memory controllers and the higher level system, but I don't have time to go into it. Yes.
You said that this occurs when you violate the timing.
For this one, yeah, D-range, for example.
Is that
Yeah.
the kind of thing that you could do with like the experimental setup that you showed earlier with the FPGAs, stuff like that, or is there some way to do that more softly?
Unfortunately, not with the published APIs of existing systems. Some systems have hidden APIs where you can do that through the software, but they don't tell you how. If you work at a company, work at that company that has designed the memory controller, you can do it. Yeah, I mean, ideally, in my opinion, yeah, you should be able to do it in a real system also. There's no reason why not to, but it complicates things, of course, right? But yeah, our setup, we can do it for freely. So if you want to do studies, you can take our setup and do all of these studies. In fact, the PyDRAM framework comes with an implementation of D-range. so you can actually use it directly. We actually released the implementation of QuackTRNG very recently also. So you can actually, a lot of these are open source right now, even though they're not written over here, they're released. If you go to our GitHub, you'll find these. I'm a big believer in open sourcing things. Okay, so, and then end-to-end system design is important, as we discussed. So I will very briefly, these operations you can actually do in other memory technologies also. As I said earlier, I believe all memory technologies have computation capability, even though they're designed as memory. Flash is interesting because in Flash, it's very similar. Even though the operating principles are different, if you concurrently activate two rows, two word lines in the same block in Flash, it turns out you get a bitwise AND function. It's not a bitwise majority or bitwise something, it's a bitwise AND. If you concurrently activate two rows in different blocks in Flash, it turns out you get a bitwise OR function. So you can do bitwise AND and bitwise OR in Flash. If you want to know exactly how that works, you can take a look at this paper, or we can cover it if you're interested, but we have other things to cover also. So basically, in Flash, you get bitwise AND and bitwise OR almost freely. In fact, it's not just bitwise AND of two values. You can activate concurrently 48 rows concurrently in Flash in a single block, and you get the bitwise AND of 48 values. So this scales up nicely in Flash memory. This doesn't happen in DRAM. In DRAM, you get some randomness, basically, as we discussed, right? Once you go over 3. But in Flash, you can get the AND of the 48 values. So you can actually do even larger bitwise operations in Flash. And this enables even higher performance. Clearly, with larger data sets, I think doing this in storage is a good idea. And I think we need to look more into the storage going into the future. Even though the latencies are high in storage, the processing capability is also quite high. And you may wonder, what about NOT, right? NOT is actually very easy in Flash. You already have a technique called inverse read in Flash. Whenever you read a value, you can actually get the complement of the entire page in Flash today. So you already have NOT today for free, let's say. But AND and OR were not well known, so we showed that. So again, it's the same thing. You can map any application over here. Okay. And the energy savings and performance improvements are even higher in Flash. Okay, let me also mention non-volatile memories. I'll briefly talk about non-volatile memories over here, not go into a lot of detail. But this is a work that showed that you could do bulk bitwise operations like row clone and majority, etc., in non-volatile memory technologies. And essentially, they do the same thing. They do n-row bitwise operations. And you can take a look at this work. I'm not going to go into detail, but they show significant, very good results also in terms of performance energy improvement. Non-volatile memories also enable some other operations that are not possible, in DRAM or Flash because of the structure. So some emerging memory technologies have crossbar array structure, especially these. And these crossbar arrays can be used to perform analog dot product computation. How many people know about this? Okay, a small fraction, or maybe people are not raising their hands. So basically, you can operate on multiple pieces of data using Kirchhoff's laws. It's an analog computation. And the basic principle is the current in a bit line is the sum of products of the word line voltage times the conductance of each cell. Conductance is 1 over the resistance, basically. And computation is done in the analog domain in this crossbar array. So, of course, you need to convert from digital to analog to digital in order to get the results. So you need digital to analog to digital converters to be able to do this. And that becomes a big overhead, actually. That's the downside over here, I see. In DRAM, this conversion is already there. Because DRAM is supposed to output digital values, right? That's why you have the send-sum spire. So we're leveraging the existing analog digital conversion infrastructure in DRAM. We're not adding anything new. But here, if you're doing this, you have to add something new, because these don't necessarily exist in these technologies. Sorry, I waited too long. Yeah, so this is a pictorial. Okay, this is a pictorial view of what's happening. So the multiply and accumulate operation. Okay, this is working right now. Essentially, due to Kirchhoff's laws, the current here is the sum of currents coming from I1 and I2 over here. And I1 is really the voltage over here, voltage in this word line times the 1 over resistance of this cell over here, which is called G conductance. And I2 is also similar here. Basically, you get the multiply and accumulate operation over here, as you can see, right? And if you do it over here, each of these bit lines provide one value and essentially you have a vector matrix multiplication. That's the idea. And this is just an animation that shows that, which I just said. I1 is the sum of, I1 is essentially the dot product of V and R values over here, like this. Okay. Yeah, this is basically, if you want to map this operation, you just feed I's, the inputs here as voltages over here, and then multiply them with the weights, and then you get the output values. Makes sense, right? Now, this, of course, requires the analog digital converters over here, which I didn't show, but those are the overheads. And the downside here, well, the downside in any analog computation, including DRAM, is reliability in general. How reliable is the computation? And here, if you increase the size of the array, like the length of the bit line and the length of the word line, reliability, of course, reduces, right? There are other effects like sneak path currents that we don't have time to go over. Yes, please.
So in this instance, in order to set these weights, so to speak, you need to change the resistances.
Exactly, yes.
So how do you do that?
So that's this is how these memories operate, basically. They're called resistive memories. Fundamentally, the way they operate is you need to have a way of changing the resistance of the cell. And in different memories, there are different ways of changing the resistance. But this is well known, let me put it that way. But different technologies have different ways of doing it. For example, in phase change memory, you need to melt the material, phase change material, to a certain level to actually set it to 0 or 1, for example. Yeah, sure. So it's fundamentally different from DRAM in that sense. DRAM is charge-based, these are resistance-based. And the reason why you can do this is because they're resistance-based, actually. There's no charge involved here. Charge is very hard to handle. Resistance is easier to handle for this purpose. And these are some papers that I would recommend if people are interested in it. There are a bunch of papers that look at this. These are earlier, like relatively earlier works, but there are a lot of works actually right now in, for example, circuits conferences that show prototypes of these devices. So people are actually trying to build prototypes of this. Okay, I don't have more to go over here. Any questions? Otherwise, we're going to switch to processing near memory. Yes, please.
So is there a challenge getting the data
Sorry, I cannot hear.
How easy is it to get the data that you're trying to process in the
Like here, for example?
general?
Oh, in general, yeah, yeah. I mean, that's important, certainly. How, like, what do you need to do so that the data is in the layout? So we actually covered that a lot in the SimDRAM paper, because your data needs to be vertically laid out in your so that you can do bit serial operations on the data, and we cover how to do that. And sometimes you need vertical data layout. Sometimes you want the data horizontal, meaning like 32 bits of the same number should be horizontal in a normal CPU, right? You think of this horizontally, 32 bits together, and then you add another 32 bits to it. Here we think of it as vertical. And then you need to transform the data. So we have a transformation unit that we add to the CPU so that you can do the transformation between one layout to another layout. So this is a real challenge, basically. How do you get it to the right layout? That's true everywhere, I think. Okay. Any other questions? Yes, please.
So these technologies are mostly for main memory, right? Are there any similar paradigms for something like SRAM or?
Oh, you mean the sort of in-memory operations? Yes, yes, actually. I didn't cover SRAM. I think SRAM is certainly interesting, but there are very similar operations that were proposed for SRAM, like bitline computing for SRAM. It's called compute caches. One work is called compute caches, if you're interested. Yeah, there's a similar line of work that's also proposed for SRAM. I think it's certainly interesting. In the SimDRAM paper, actually, we talk about that, and we compare the SRAM approach versus the DRAM approach. When your data sets, of course, fit in SRAM, then that's a good idea. But when your data sets are very large, it becomes difficult to manipulate things in SRAM. Then you need to partition your data set somehow, and yeah.
Also, the SRAM is much closer to the processor, right?
Yeah, the benefits you get are lower. Yes, I agree with that. Yes, it's much closer, but you still get some benefit actually because you don't move the data within the processor, right? Especially with very large caches. time to access the caches maybe 50, or as we discussed earlier, right, 50, 60 cycles. So you save some of that. But yeah, bigger benefits come when you go farther and farther. In fact, as I said earlier, if you're doing it at the store, that's where some of the biggest benefits will come.
This
Yes.
is kind of a follow-up question, but has there been any kind of like study on a framework for streaming through multiple levels of in-memory compute like that? So imagine you had processing using memory at DRAM and also at various cache levels, and streaming data through the DRAM, through the caches into the processor as kind of a whole pipe.
Yeah, that's a good question. I mean, not that I know of. There's potential for some work, I think. Yeah. It's good to think about it.
But in the end, if you do that, you are forcing the pair of KV, right? So you
Yeah.
have a pair of in-memory compute, right? So-
Yeah. Yeah, I guess it depends on what benefit you get out of that. If there's some benefit to it, it would be interesting to examine.
But I assume there's some operations that
Yeah.
don't fare too well in processing using memory, right?
Yeah. So certainly, okay. If you're thinking of that, some operations like complex operations can be implemented near memory, for example. I think the combination of processing using memory and near memory is a very good idea, because some operations are not efficient in using memory, even though SIMDRAM exists or lookup table exists. Some things are really not efficient. You just want logic there to do this thing quickly. So in that sense, I think near memory helps. Okay, so let's jump into near memory. I think we're still going to think about memory as an accelerator, and we're going to add compute capability in memory, but this could be a processor right now. This could be a lot of logic. We have a lot more room. Here I'd like to talk about applications, because the question is, okay, if you're going to add processing near memory, what do you do it for? Right? What benefits and what doesn't benefit, and what kind of computation capability is good? There's a huge design space here, clearly, and I'm going to show you some examples of the design space from both memory and storage. Let's start with the memory part. This is the work that we did we started almost 10 years ago, actually. It was eventually published at ISCA 2015, but that doesn't mean that it was not submitted earlier. It was rejected multiple times. A lot of these works are like that. So if you get rejected, don't get discouraged. It's life. But we wanted to look at these graph analytics workloads that are clearly important, and graphs are growing larger. And these are some numbers circa 2015. For some reason, Facebook has much more users right now. I don't know why. I don't understand the reasoning, but it exists. I use it also, but not that much. But basically, the issue with graph analytics is usually your pattern, your graph access pattern has a lot of randomness. It's not completely random. You can actually get some locality out of it. But as your graph grows larger and larger, there are random portions. And we see a lot of that. And you get frequent random memory access and little amount of computation to cover for it. And because of this, your cache hierarchies are essentially not very efficient, right? Your cache hierarchy builds on locality, and you're not exploiting that locality well. So we decided to look into 3D memory plus logic inspired by the hybrid memory cube. Here we have a logic layer underneath memory layers, and the logic layer has high bandwidth, low latency connections to the memory layers. The details are in the paper in terms of what are the latencies, bandwidth, but I'm going to show you one number later. And you can implement anything in the logic layer, basically. That's our assumption here. You can implement a good enough processor here, let's say. And I believe that's true, actually. And actually, this is just the beginning of it. People are looking at true three-dimensional technologies. The next technology from Stanford, for example, looks at true monolithic 3D stacking with even denser connections. You don't have through silicon vias, you have vias, basically. These are interconnects that are actually very dense. So I think those true three-dimensional technologies are going to change the game even more. But using this, we basically design a distributed system accelerator for graph processing. You can think of this as a primitive GPU. Like in the past, what GPUs did was you offloaded some computation to the GPU, and GPU executed, then returned back. It's true still like that, kind of, but it's evolved, of course. Here, you can imagine that we have an accelerator. We partition our graph on the distributed system. The accelerator is a distributed system of these three-dimensional cubes. They're interconnected in some manner. You partition your graph, and you offload your graph computation over there, and then graph traversal happens, and it returns a result to the CPU. That's the idea over here. So the question is then, how do you design this accelerator? So there are no coherence issues because everything happens in the accelerator in terms of graph processing. It's all physically addressed, so it's painful to program a little bit, let's say. And it's programmed using message passing. We basically assume that you move the function to the data as opposed to data to the function. That's the idea over here. So we have these distributed, like interconnected 3D cubes. Each cube looks like this in the logic layer. In the logic layer, you have a bunch of vaults, and each vault you have an in-order core and some memory controller, etc. And in-order core houses the data on top of it, on the stack on top of it. And if someone wants to update a graph location, they need to send a message to the core that houses that graph location, graph node, essentially. That's the idea. So all of the updates happen by sending the function to the data where the update is supposed to happen. So you need to send the temporary values, of course, right? Some data needs to move. It's not like nothing moves. But this reduces the data movement significantly. It's message passing based. So it's essentially a distributed system. You program it like a distributed system, physically addressed. And there's some interconnection network, as you can see, within the cores inside the logic layer, as well as across different cubes over here. So that's basically it. And then we add some prefetching mechanisms so that we can prefetch the graph nodes that we're going to process later on. So this is a full system design. It has a programming model. It has some ISA changes. It clearly has some hardware changes to support that. So I don't have time to talk about all of these, but these are the key takeaways. Yes. Yeah. So there's no assumption, but basically you don't get huge benefits if your computation, there's not some there's not local computation. There should be some locality, right? Basically, that's the assumption. That's the hope.
Yeah.
And that hope can be satisfied with good graph partitioning algorithms. We examine that in the paper. If your graph partitioning is better, such that it improves the locality within the cube, you get much better performance. So graph partitioning is a hard problem, I know, but there's some, basically not everything is completely random.
Well, the point that I'm trying to get at is, even if there's lots of locality, eventually you need to do things like reduction.
Absolutely, yeah. Yeah. And those things, I mean, those things are very hard for processing in memory, clearly, right? When you aggregate the data in one place and do a lot of operations on it, those are the things that are tough for processing in memory. You need to, that's where the interconnect actually makes a big difference over here. Yes.
So, I guess just one thing I'm seeing is like, you can see there's got like, there's one cube where there's two nodes in the same box.
Yeah.
So if you've got like some algorithm where like it's making the size of the amount of data representing different nodes be bigger, much complicated than that things. You're saying that all of like this isn't physically addressed. Right? So if you're having to like relocate nodes, what's that do for the programming model?
Well, if you need to relocate nodes, you need to change the physical addresses, right? So I think it's not easy, but doable, basically.
So I guess it's like a question of like having some kind of set up all that.
Yeah. I mean, here we assume there's no, we just do hand programming. Everything is hand programmed. But yes, a compiler can optimize these things, right? For sure.
But yeah, it's like that.
Yeah, this is just a proof of concept as opposed to a full system that can be used by someone. And it's not easy to program, no question about that.
Yeah.
But I think early GPUs were not easy to program also. Yes, please. Yeah, certainly. And this is our work. Later work after this improved a lot of these issues that you mentioned: graph partitioning, load imbalance, support for aggregation, for example, things like that. Yeah. So it could be imbalanced. But I'll show you results. Even with all of the potential issues, we get significant performance and energy benefits. So let's take a look at how things are done. So these are the systems that we compared to at the time. You can see that there's a processor memory dichotomy. The blue pieces are all processors and the other pieces are memories. But Tesseract doesn't look like that. Processing and memory are coupled, right, in the same cube. And then you have a distributed system of cubes, basically. So fundamentally, this is different when you look at it. And as a result, you get high amounts of bandwidth exposed to the processors, 8 terabytes per second. This is old numbers, as you can see, right? This is from circa 2013. Today, you get 8 terabytes per second already, but this would get you even more, basically, because you're tightly coupled with memory. And the performance results that we demonstrated were actually quite good. On average across 5 graph processing algorithms, we get about, with all of our optimizations, we get about 13 to 14x. And again, this is work from 2015. There's a lot of work that built upon it and showed that you could get close to 2 orders of magnitude today. Again, by optimizing the system, like with what we were discussing earlier, graph partitioning, interrupt handling. There are some interrupt handling that you need to do over here that messes things up, load balancing, aggregation, support for a bunch of different things, basically. If you're interested, you can find those works also. I think one of them is called Graph P, Graph Q, things like that. These are actually interesting works. Okay, and the energy reduction is also quite significant because you're reducing the data moment significantly. And the data moment cost is also lower within a cube. So we showed more than 8x energy reduction. And again, later works improved this to almost close to 2 orders of magnitude. And this is, again, there's no trade-off. Performance improves, energy improves at the same time, right? So it's nice to have almost close to 2 orders of magnitude improvement in both over the course of, let's say, 10 years or so on this application. And this is near memory processing. Right? And this is the paper if you're interested. There's a lot more that I glossed over. Okay, let me give you the high-level idea of this one also. This is much more recent. We did this work in ASPLOS in 2022, this year. And we wanted to look at in-storage computing, especially in the case of genomic data analysis. And here, we're really targeting very large data sets that don't even fit in memory. So you don't even want to think about doing in-memory computation. I mean, you could do it, no question about that, but you would be a lot more efficient if you actually kept the data inside the storage and did some filtering inside the storage before moving into memory. Let's take a bird's eye view to the system. So if you look at this, we have ignored the storage system so far, but this darkness is actually very important. So how do we do genome sequence analysis in a conventional system today? We basically move everything from the storage system, from the sensors to the storage system to the computation unit. And then we do some sort of alignment. This is the particular operation we're accelerating. Don't worry about that. Basically, you're comparing. It's an approximate string matching comparison of pieces of the genome to a reference genome. You do it in the, yes. Well, we have other algorithms, but Smith-Waterman is one algorithm to actually achieve that, yes. But you both pay the cost of computation overhead and data moment overhead. Now, computation overhead, a lot of people have worked on it, including us. You have heuristics, accelerators, filters. You try to get rid of computation as much as possible, make it more efficient. So that addresses the computation overhead part. That just makes data moment overhead even worse, actually. It's a much larger fraction of your execution time now. That's one of the reasons why things get dominated by data moment today, because we're very good at computation, right? That's another example. So what we do in this work is filter in the storage system, do a very small amount of computation, simple computation, so that you quickly decide which reads should really be processed by the heavyweight computation units. And I mean, you can imagine doing this for other applications also, but genome sequence analysis is clearly interesting. You only send a small amount of work to the computation units. A lot of the work is done by the storage system. That's the idea. So what are those works? This is where actually the important thing about understanding the algorithms comes in. What can you filter out? It turns out if a read piece of a genome you've sequenced matches the reference exactly, you can figure that out very easily on the storage system. It's just a very simple comparison, right? So exactly matching reads are easily found out in the storage system, and you don't need to send them to the computation. You just need to send an indication of which ones are matching, for example, so that you can, in the end, the computation pieces together everything, right? That's the idea. And also, if a read is completely off, so when you do genome sequence analysis, you sequence the genome that you're examining, and you try to match it to a reference genome. And if they're completely different from each other, or significantly different from each other, that read is deemed useless, let's say, because that's not an interesting part that matches. As a result, we call it non-matching reads, and these are also relatively easy to determine, it turns out. And these are very simple accelerators that you can add to the storage system. Maybe there are other filters that we did not discover, but these are the two things that we have discovered and implemented. So that's the idea over here, basically. So this also addresses at least data moment overhead partially. And in the paper, we show results that are quite significant. You can see that they range from 40% speed up to 33x speed up. And energy reduction is from 4x to 30x, or almost 30x. And again, this is not a trade-off. Both performance and energy improves. This is also the reason we have these huge ranges is because different data sets have different fraction of exactly matching reads or non-matching reads. So it really depends on the use case of basically the input sets that you have to the system. But I think this sort of approaches are going to be a lot more interesting as well. I mean, you can imagine doing this for databases also, right? In the storage system, many applications could benefit. I feel that storage system is, when I say darkness, when I call it darkness, it's really darkness. I mean, people have optimized the storage system in many different ways, but the computation part has not been thought of as much, right? Even though there's a lot of opportunity over there. Any questions? And this is the paper. There's a lot more detail than we can go into clearly in the paper. Okay. Let me give you a little bit more about what we did with Google. I won't go into a whole lot of detail again because we've covered a little bit of this. We basically examined these applications. So our goal here was to really understand the effect of data moment on mobile systems. And these are mobile applications that are heavily used. If you're using Android phone, you're using Chrome, for example. I use Chrome on my laptop, but all of these are used heavily. In fact, Google, to accelerate video encoding and decoding, they design specialized accelerators, right, on the for their data centers, and that's employed by YouTube and the Google data centers a lot. And we look at some of these accelerators actually in this work, or earlier versions of those accelerators at least. So basically, we show that more than 60% of the total system energy is spent on data moment in these real workloads. And we wanted to understand how can we get rid of that data moment. And we're going to use near memory processing again. And the observation we had in this work is often very simple functions lead to a significant fraction of the data moment. For example, in Chrome browser, when you're loading a web page, a lot of copying happens. Copy is one example function. Compression, decompression. In the Chrome browser again, what happens is some of the unused tabs get compressed and put into memory. And when actually you switch to that tab, they get decompressed. And decompression becomes on the critical path. And you can perform that decompression inside memory much more effectively. In fact, that's what we show in this work. In terms of, for example, motion estimation is another one in video encoding and decoding. That motion estimation tends to be very heavily data intensive. And if you offload it to memory, you can do it much more efficiently. Maybe motion estimation is not the simplest function, but you could do it with near memory processing, right? That's the idea. So that's the key takeaway. You can offload these simple functions to memory, either to simple low power embedded cores, which we examine in this work, or small fixed function accelerators that are designed for this purpose, which we also examine in this work. And we show that, again, average across all of these workloads, on average, you can improve energy and performance by 2.3x and 2.2x. This is nothing like 14x or 100x, clearly. But we're not also changing the system significantly, right? We're just offloading some specific functions because their data moment remains in other parts, other functions. Yes.
These numbers go from like a simulator or making an actual chip.
Yeah. Yeah. So that's a good question. I mean, we don't have the real chip here. This is all simulation, basically. So I don't know the answer to that. I believe once you make the real chip, maybe the initial numbers are going to be lower than this. But over time, as you optimize things, in my opinion, you can actually get to much higher. I will show you some real results with the UpMem chips. Not exactly these workloads, though. Yes, please. So in this case, we compared with CPUs with SIMD units. Yeah. GPUs, we did not compare to because the workloads that we're accelerating are not on a GPU. That could be a separate comparison point, but we had to port the workloads completely to a GPU if you had to do the comparison. Okay. Well, think that, okay, time constant is. So let me give you another example. There are many functions we examine, and the paper covers them, but in TensorFlow Mobile, we examine this also heavily, especially for inference. We didn't look at training in this case because these are mobile devices that we're not doing training at that time. Today, I think with federated learning, etc., mobile devices should do some training also, clearly. But basically, we found out that a significant fraction of the inference energy on state-of-the-art networks is spent on data movement. And a significant fraction of that data movement comes from very simple functions, in particular, two functions in this case. And they're both data manipulation functions, packing or unpacking of the data, or quantization of the data, which are both heavily used in neural networks today. Again, I had some other slides, but I don't have them right now. Basically, packing and unpacking reorganizes the data so that the next step in the processing can nicely operate on the data with more parallelism, for example. And that is very simple operations. It's just simple shifting, multiplication, etc. Quantization is basically chopping values. You convert a 32-bit floating point number to a 4-bit integer, for example. And that is also very data intensive because you feed a lot of data, a lot of 32-bit operands to this unit that's very simple. And if you do it on the memory side, you get rid of a lot of that data movement and you supply only the quantized data back, right? That's the idea. Yes. Yeah. Yeah. So what happens in TensorFlow in some of the mobile devices, they optimize even for that basically. Okay. So basically, you may start with maybe not 32-bit floating point. You may start with 16-bit integer, and you basically downsample it to 4-bit integer.
Do you do this thing online? I mean, it's offline, right? So one line.
Yeah, that's a good question. I think it depends.
If you do online, of course.
Yeah.
This optimization is used by, but you need to apply.
I think sometimes they accumulate the values, but then
Yes.
so then even if like the like general stuff, it's like accumulating onto the event.
Yeah. Exactly. So it happens online. I mean, not all cases are online. Of course, some cases you can get away with doing offline, but in the workload we examine it's online. The stuff is in memory, and then you basically don't use stuff that you're not supposed to benefit from, let's say. They try to optimize for it. But that's a good question. I mean, if you can do it offline, right? Yeah.
I have a student working on that.
I see.
I don't remember the
I see. Okay. Yeah. There's more functions in the paper. And if you're interested, this paper actually has a lot of analysis data on interesting workloads, let's say. I wish we were able to examine more workloads, but this is a course of 2 years and a lot of effort. And 4 workloads was, it'd be good to have more workloads always. But I'm going to show you another work we did with Google on neural networks specifically. But that's a slightly different flavor. Okay, so there's a lot more to talk about. Let me give you a flavor of, you can do this in GPUs also. So GPUs were brought up earlier. But you can actually have a main GPU that's compute oriented, and you can have smaller GPUs in the logic layer of these memories. And you can offload the data intensive portions of the functions to these smaller GPUs over here. And we actually looked at this together with NVIDIA. And I'm not going to go into details, but we were quite ambitious here. Our goal was to transparently offload GPU kernels, decide which parts of a GPU kernel should be executed in the simple GPU in the logic layer, versus which parts should remain in the main GPU in the middle over here. And our goal was to actually do it transparently to the programmer, which means a compiler needs to do it. And we didn't build the complete compiler, but we built the algorithms to decide. And in the end, we gained some performance. But if you do it completely transparently, the way we do it, the performance improvements are not, let's say, 2x. It's more like 50–60%, which is not bad. But I think you need basically more. You need to do more if you want to get more. So there are other works that I'm not going to cover. We've been looking at 3D stacked memory using accelerating pointer chasing. I was joking, we were doing pointer chasing by going through the elevators. You go through one elevator and that points you to some other elevator. That clearly has a lot of latency, right? And doing it closer to memory improves performance also. So it's interesting. This work also looks at how to do virtual memory, which is kind of an elephant, a huge elephant in the room that we didn't discuss. how do you just deal with virtual memory on the memory side? Because you have virtual addresses in the CPU, you offload something to memory. What addresses do you use? If you use virtual addresses, who translates them? It's a huge mess, basically. I think virtual memory is the biggest mess when you want to distribute programs, especially to the memory side. It's already a mess, actually, even if you don't want to distribute programs, right? In a large-scale system, virtual memory doesn't scale very well. So I think we need to rethink virtual memory in general. But this is a tough area, let's say. This paper introduced a virtual memory model where part of the virtual memory is reserved for in-memory computation. And I don't think it's the greatest solution, let's say, but it's a practical solution. Okay, so there's more work. You can do this transparently. You can actually accelerate prefetching. This is a work that I briefly mentioned earlier, but FPGA-based acceleration of weather modeling, climate modeling workloads. I mentioned the string matching. So there are many workloads that you can accelerate that we don't have time to really go over, but there's a lot of papers that are written on this topic, as you can see. And this is the paper that we looked at earlier when we wanted to look at the data sets. Here, we tightly integrate base calling and readback, multiple steps of genome analysis in a single in-memory accelerator. And that actually reduces a lot of movement. Today, these genome analysis steps are done in different devices, actually. Okay, so we also looked at time series analysis. Like there are many workloads that are quite data intensive, actually. Once you start looking at workloads, you're amazed that time series analysis is amazing, actually. This basically, you get data that's collected in many fields, like astronomy, right? People in astronomy collect a lot of data. And what they're looking for is anomalies in the data. So you normally run algorithms called time series analysis. There are multiple interesting algorithms here. And you try to find the anomalies on streaming data usually. And this is very, very memory intensive. So we see significant improvements over here also. This is something also interesting. Recently, we looked at graph pattern mining, again, graph analytics. And here, we wanted to maximize the bitwise operations, just like other people did for databases and web search. And here, getting graphs also, you can also do that by formulating the graph processing as a set operations. You're doing set operations on the graphs, essentially. And you can actually formulate an instruction set architecture that's based on set union, set intersection, set operations. And this maps very nicely to both near memory as well as using memory acceleration. So in this paper, we look at both processing using memory as well as near memory. So again, I don't have time to go over it. These are full system designs, but I like this one also. Well, maybe the computer doesn't like that one. Okay, so this is also interesting. Again, here, if you look at processing in memory for databases, hybrid transactional analytical databases. So usually people design databases today to be hybrid. Transactions and analytical queries are handled differently. Transactions tend to be very CPU or compute bound. Analytics is basically you're scanning a huge database and you're looking for something in the database. Database scans, for example. That tends to be very memory bound. And if you can, here we partition the database between near memory processors as well as compute-centric CPUs today. And we optimize things, but I don't have, again, time to talk about it. But this is just to show you that there's a lot of work going on. There's a lot of applications, and I think we need more work, frankly, in this area. Let me talk about this one, because this is interesting, and this is, let's say, something that's very difficult to do solely in academia. We did this together with Google also through an internship, and say it again.
No.
Okay.
I did this paper last year.
Oh, okay. Oh, in PACT. Okay. I see. Okay. Yeah. It was probably not very well written, sorry. We tried to make it better written for the final version. Yeah. So basically, we worked with Google, again, over the course of some time over here. These things usually take time. And this is the summary. We examined 24 Google Edge models. These are models, neural network models that Google uses in their edge devices. They're proprietary, unfortunately. We cannot disclose them, but we can disclose some of the properties. And these are different models, as you can see, transducers, long short-term memories, etc. And we analyze Google's edge TPU design that they have. And we find out that basically it's not very efficient, very inefficient, actually, because a lot of these workloads are very memory bound. And we have some numbers in the paper also showing that that 60% number is actually not that big. So some of these workloads are completely memory bound, basically. I'm going to show you that a little bit. So the main reason is the accelerator is compute-centric, and it's designed essentially monolithically. It doesn't cater for the different properties of these different workloads. So here we introduce, so it doesn't account for heterogeneity in these workloads, let me put it that way. So to account for that, we create some heterogeneity in the accelerators. So we design, in particular, 3 accelerators. One is compute-centric, similar to the HTPU, but much smaller, because it doesn't need a lot of memory. It's catering to these compute-centric, compute-dominated parts of the workloads. The other 2 accelerators are memory-centric because they're catering to the memory bound pieces of these models. And we show in this paper that you can improve both performance and energy efficiency average across these workloads by about 3x, which is good. Again, no trade-off. Performance improves, energy improves. And to our, let's say, surprise, we also showed that you can improve area efficiency. So a single monolithic accelerator, as it's designed today, is over-provisioned. 3 accelerators together are smaller than the single monolithic accelerator. You could argue that, okay, maybe that was the monolithic accelerator was a bad design, etc. But that's how it is today, at least for these workloads. Yes, please. So basically, I'll show you. It has very low flops per byte, for example, some of these layers. Okay, so these are some of the models that we examined, 24 different models. And we characterize these models in terms of flop per byte, as you can see over here, and the parameter footprint. And they're very different from each other. For example, LSTMs and transducers especially behave very differently from convolutional networks. So there's significant variation in terms of layer characteristics across the models, across different types of neural networks. And within the model also. So even within each model, layers exhibit significant variation in terms of characteristics. For example, this CNN5 has different behavior in its layers, in its different network layers. This CNN model has also very different characteristics, even more different, widely different characteristics than this one, as you can see. So I can see significant variation in terms of multiply and accumulate intensity, as well as flop per byte across different layers of the same model. So these are orders of magnitude, as you can see. So what we propose in this work is, instead of having a single accelerator for all of them, all of these different models, why not have families of accelerators and a runtime to decide where each model that belongs to a family executes. So in this case, this is, for example, accelerator 1's similar to this one. This accelerator 2 is near 3D stack DRAM, so it's a near memory accelerator. This accelerator 3 is also near memory accelerator. And we customize the data flows to the characteristics of the models. So it's not just compute-centric versus memory-centric, but we customize the data flows so that it's more customized for the characteristics of the layer family. And the paper has a lot more detail than I can discuss. So how do you identify layer families? Basically, you do a clustering in this particular case. Just to give you some examples, so families 1 and 2 have low parameter footprint, high data reuse, and high MAC intensity. They're essentially compute-centric in that sense, because you can see that there's high reuse, right? Traditional accelerator would work. But some other families have very high parameter footprint, low data reuse, and low MAC intensity. And if you look at the results, especially the memory-centric, memory bound, memory bound layers improve in terms of performance even more than others. But I won't go into a lot of details. And this is throughput improvement. Any questions? Yeah. I think there's more work to be done. I mean, we're just scratching the surface over here. I think the scheduling over here that I didn't discuss much is really important. And how do you do the parallelism? How do you take advantage of the parallelism of heterogeneous accelerators is really important. We didn't have time to really study those in a whole lot of detail. But I believe there's more over here. And then the question is, of course, how many accelerators do you design, right? Is it 3? Is it 5? Is it 10? Can you make them somewhat reconfigurable to actually take advantage of a broader family of accelerators? So there's a huge design space over here, in my opinion. We're just scratching the surface. Yes, please.
Yeah, so I was going to ask, because obviously the focus of this talk is we want to minimize data movement.
Yeah.
But anytime you do layer n on one accelerator and layer n+1 on a different, then that's
Yeah, I need to communicate.
a fair amount of communication. So did you run into, or did you look at cases where it's like better to run layer n+1 on a suboptimal accelerator?
Yeah.
so you save the data?
Yeah. We looked at those, and in some cases, this is not optimal. What we did is not optimal. I think you can do better by doing those. We saw those cases, but again, we didn't have time to optimize everything. But I think there needs to be a more global optimization also, right? That's why this runtime, the scheduler, is really important in my opinion. It needs to look at communication between the different layers as well, for sure.
Actually, this part, actually, there have been a couple of related papers. I don't know if you sent also similar, but
Yeah.
I was involved in similar paper.
I see.
With this kind of-
Okay, was it accepted?
No, I don't
It was not my paper, so I don't know. I don't.
But I can tell you, I actually do that. This is a trend that needs to be considered.
Yeah.
Completely agree.
Yeah, exactly. I think, as I said, this is just scratching the surface. There's a lot more work to be done. But I believe that this is really the right approach. I think having a monolithic compute-centric accelerator or monolithic data-centric accelerator is not the right thing to do. We really need more heterogeneity, because this is already happening in CPUs, right? Why not also in accelerators? We have heterogeneous CPUs. People have finally come around to actually have heterogeneous CPUs, let's put it that way. If you really want to specialize beyond just a general neural network accelerator, right? But neural networks are also very different from each other internally. Yes.
And there are ways that you think communicate this kind of architecture, like up the stack, as it were, to say to neural network designers, it's like, oh well, I don't know, layer 1 is like this, layer 2 you can make a different shape.
Yeah.
Maybe if you made it like bigger, whatever, it would be faster because you're not having that overhead there because you run this hardware.
Yeah.
Like I guess like you've got this architecture, there's like all these questions about scheduling. Also these neural networks aren't necessarily needing to be fixed either. So you need this architecture approach.
Yeah, I think so.
Asset.
I mean, I think it's like any accelerator design, right? If the developer or software designer is aware of what's going on underneath, they can optimize their software. And we didn't do that again here. We just took the layers and tried to fit them to an accelerator, but you could also do more, right? And you keep optimizing that loop. I think it should be done also. Yes. That's a good idea. Well, again, computer may not think that it's a good idea. Okay. We've already talked about this work, and I'm not going to talk about it again. But I think a lot of these works show that we should really think across the stack, right? In a lot of these cases, we're changing the algorithm. In some of these cases, we're looking at the different hardware software interfaces, right? And different devices also maybe I shouldn't call it different devices, but different ways of using the devices, like in DRAM. So I think there's a lot of opportunity. But also some of these ideas are simple as well. Like the row clone idea, I go back to that, right? That is doable in existing chips, existing DRAM chips. It's just copying. And we are able to actually design an FPGA-based prototype to do it. And you can actually take that FPGA-based prototype and run your application with some pain and see how much benefit you get from row clone. So if this is like that, then it's not that hard to do it, right? If we can do it, then yeah. So I think there's a lot more over here. And again, we cover a lot more in this primer paper. We also have some other papers that you may be interested in look at. Here we focus on the workload and programming aspects, which segues us to adoption challenges, of which there are a lot. So it's always easy to design hardware, but getting it adopted is the hard part, right? And I think we've seen that a lot in the history of computing. Any questions before we jump into it? So adoption challenges, I think, of new paradigms and new hardware is always about software. You need to somehow get the software base running, right? The question is how. And I don't know the answer clearly, but I can list you the challenges. So these are some of the challenges. I think what type of applications benefit a lot? What type of software benefits? How do you ease programming for many people? The masses of programmers. I think this is where GPUs were quite successful. They eased the programming, especially with CUDA, for example, and maybe other things are needed to ease programming even more. But basically, we need interfaces, compiler, and hardware support to ease the programming. System and security support, some things we did not fully, we touched upon, like coherence, virtual memory. I think these two are actually the toughest ones. Virtual memory being even tougher than coherence, in my opinion. But other things like synchronization, we've been working on all of these with limited success, let's say. How do you provide isolation if you want to run multiple things on the memory side? That's something that's been examined, but not to great detail, and interface again. And runtime and compilation systems to decide what should run where. That's really critical, I think. I mean, you can have the compiler, have the programmer decide this also, but that's probably not a good idea, especially if you have many applications running and sharing things. Data mapping, like how does data get mapped, interleaved? How do you convert from one mapping of data to another mapping of data? Today's data mapping is completely processor-centric, right? What we do is we interleave our cache blocks across many different channels, for example, many different banks. But that's not friendly to memory-centric execution, clearly. For memory-centric execution, you want the chunk of data in the memory bank and not across different memory banks, the chunk of data you're processing. So these are some example issues, and access and sharing control, and also infrastructures to assess benefits and feasibility of the approaches. And I think this is very important. That's one of the reasons why we've been developing and pushing out the infrastructures as open source. Here, where open source is important. I mean, here you can see that there's no hardware, right? Maybe hardware support for these is interesting, certainly. I mean, coherence, hardware support for coherence is important. But I'm not talking about hardware to do processing in memory. I think those are not adoption challenges. Those are doable. Some of them require creativity, of course. For example, how do you do bitwise operations, etc. There are challenges over there, but they're not adoption challenges. I think they're the key is getting those computation units adopted in the higher system level. So I believe maybe the most difficult adoption challenge is the mindset. And this is very tough to solve. So here, everything we do is kind of compute-centric today, right? And we're kind of shackled in history. So over the course of 70 years, business segments have developed. You have computing, and then you have memory, and they're basically completely separate from each other. Even if you look at companies that do both computing and memory, their business units are completely separate from each other. Like Samsung is a great example. I think Samsung, if they can realize how they can communicate between these business units, they can dominate the world potentially. But they have a GM unit, they have a processor unit. They clearly design processors, right, in their cell phones. But they might as well be from different worlds. So that's the idea. That's basically we have this huge partitioning across the stack. We've kind of created barriers, and then we've created bureaucracy to change the interface between those barriers. So if you want to communicate between processor and memory today, you have a very rigid interface, which is the DDR interface, for example. And if you want to change that, good luck. Because everybody will be against you if you want to change that. There's an institution called JEDEC, which is a standards institution, and they basically decide the DRAM interface, and they're basically opposed to any change almost. The RowHammer changes passed because they're very critical to the business, right? So they said, okay, we need to solve the RowHammer a little bit. But anything beyond that, that's not threatening the business or whatever, they cannot agree on. So basically, this mindset is the toughest part, in my opinion. How do you change that? And partially, there's business interest in here, right? Because people are making money, clearly. Yeah. But maybe we have a bigger responsibility to the world, right? We cannot keep wasting so much energy. This is where I get back to sustainability, right? Are we really doing the right thing in our systems by being so obstinate on how we do things today? Yeah, but that may not be enough. I don't know. Anyway, okay, so I think in the research space, we need to revisit the entire stack for sure. Okay, I will not bore you with more, but that's why I think these key applications and accelerating them are really important. We need to show more and more of these case studies. Again, I will go through these quickly. I've shown you a lot of these. I will mention that how to keep it simple is important. This is a work that I'm not going to discuss, but keep it simple means how do you integrate this into the existing programming model with minimal changes? Here we propose very similar to SIMDRAM. SIMDRAM actually builds upon this work, but basically in-memory operations should be encoded in the sequential execution stream, sequential ISAs we have. Some instructions can be executed inside memory, near memory, or in the processor. That's the idea. These are called PIM-enabled instructions. And here we actually even do even more. Basically say that these operations cannot execute on data that's bigger than a cache line. Because if you execute on data that's bigger than a cache line, you run into multi-cache line coherence issues, and you run into translation issues also. Yeah, so basically we have some restrictions. And even then we show significant benefits over here, not 2x, like 50%, 70%. Coherence, as we discussed earlier, is important. This is something that there needs to be more work on. So for example, in this work, we showed that if you partition your workload, for example, a hybrid transactional analytical database over here, between the CPU and the near memory, coherence overheads become overwhelming if you don't do coherence right. For example, fine-grained coherence like MESI, coarse-grained coherence like locking, and treating near memory data as non-cacheable, they just don't work basically. They're not very good. So we propose ideal coherence. If you magically keep everything coherent, then your performance actually improves. I mean, performance improvements here are small, but these are small data sets. That's the reason why they look small. But 50% is still respectable, I would say. But if you don't do coherence right, you don't even get 50% on average, as you can see, right? The best mechanism gets 5 or 10%. I cannot read it over here. So it's pretty bad. So it's good to look at new coherence mechanisms. Here we have a coherence mechanism where it's partly transactional. When you offload a kernel to the memory, that kernel runs and keeps track of which cache blocks it modifies. And then at the end of the execution of the kernel, it sends this information using Bloom filters to the memory, to the processor side. And the processor checks which of these cache blocks it conflicted with. It read from or wrote to, depending on the what the memory did. Basically, it does a signature comparison. And if for some reason it determines that the memory execution violated, basically create a data conflict between the processor execution, it rolls back the memory execution, and the memory needs to execute again. So that's the idea over here. This is one mechanism for helping coherence, inspired by past transactional memory type of approaches, speculative approaches. I'm not suggesting that this is the best mechanism, and this is a longer version of the paper that shows that, but we see significant performance improvements compared to existing coherence mechanisms that we mentioned. I think there's more work to be done in this area. So the downside here is, I think, complexity in general. You're trading off, you need to add more complexity to the system to keep the system coherent, right? How do you minimize that complexity? That's research. Or how do you come up with a completely different idea to enable coherence, right? So we've been also looking at synchronization approaches. I'm not talking about this, but this is also important. How do you synchronize near memory is interesting. And there's a lot of interesting data and ideas in this paper. Virtual memory, as I said, is the toughest part. I don't think there's a great solution to this other than saying, okay, this part of the memory is allocated to near memory processing units, and they have some translation mechanisms out there. Clearly, replicating the translation infrastructure to the other side is also possible, right? Basically, you have the entire virtual memory system built on near memory processors. That sounds like a terrible idea, because I think virtual memory system in compute-centric processors is a terrible idea also to begin with, in my opinion, today, because we have so huge memories and we're trying to manage them in a very small granularities, right? Page-based granularities. I think people are trying to rethink how we do this. There needs to be more effort, and replicating them on the other side is a huge overhead also. And also, how do you keep it compatible? Because these memory chips may not be used with the same ISA. Do you actually replicate all possible ISAs on the memory side? So it's a huge mess, basically, I think, virtual memory in general. So I don't know the solution to this, but I think there are bright minds over here. Maybe you can find a good solution. Maybe the solution is really figuring out how virtual memory should really work in real systems, right? Yeah. This is also one of the biggest pushbacks, actually. In general, somehow, this virtual memory is also so ingrained in our thinking that we cannot pull back out of it. Anyway, okay, so these are adoption barriers. Let's look at some processing in memory approaches in the real world. How much time do we have left, by the way? 2 minutes?
20.
Oh, 20, okay. Okay, good. So we still have some time. Any questions on the adoption challenges? No. Yes.
Can you say something? What is the timeline of How many years?
Get there, define there. I mean, solving all these challenges, never. We haven't solved these challenges with even CPU-centric systems, right? This virtual memory is a huge mess. So I would say never. Coherence is even in a CPU-centric system, it doesn't scale, right? So I'm not suggesting we should solve all these challenges to make this viable, right? For example, GPUs are a great example, in my opinion. 25 years ago, GPUs were embedded in our systems, and some people said, "Oh, can I use this for my purpose, computation purpose, other than graphics?" And those people did the hard work to actually make it happen, right? They didn't care about coherence. They didn't care about virtual memory. They said, "I'm going to take this and make it work for me." I think that's what we need, really. We need some prototypes, some real systems, so that some of these really ambitious people that really need something different because the existing system is not working for them are going to show that they are going to get that thing different. And they're not going to care about coherence. They're not going to care about virtual memory. They're not going to care about security. All they want to get is their computation to be faster and energy efficient. And the way to do it is having prototypes of these real systems. I don't see any other way, frankly. We were lucky to have GPUs embedded for whatever reason, right? Well, graphics reasons, certainly.
So the question asked, how would we have separate memory?
Well, maybe very quickly. I don't know. It depends on there. I think it depends on the inertia in industry, right? I think people are working on it and people want to have it. No question about that. But again, business disruptions can be downsides. So I think I'm very optimistic there. That's what I'm going to talk about next. Does that make sense to you? So I think once people see hardware and get hardware, and hardware is really easily accessible, I think people will do a lot of things. I think GPUs were in that area, right? Yes.
Yeah, I guess I'm going on back with that.
No.
Maybe a little there before it's like a gym purpose processing in there. Like,
Yeah.
You know, in a few years, I'm going to buy some new personal computer device, like Onur, laptop or whatever. What do you think will be like the first chip inside that that will have a processing memory component? Like, what will it do? What will be the first like GPU type thing that's doing processing?
Yeah, I don't know. I think, yeah, we'll have to see. I mean, in the storage system, for example, today you have computation capability, but the interfaces over there don't allow us. If I was a storage system designer, I would open up the interfaces and let people use it, right?
So that might be kind of the first wave that we might see, since it's easy sort of with that hardware perspective.
I think so. Frankly, I think so. Yeah. Yeah. But again, it's a mindset issue in the end, right? If storage companies don't think this way, right? They think, oh, I'm designing storage. Nobody's going to, they don't even think about compute. This is a storage. So in a sense, their mindset is a bit limited. But if I were designing with my mindset a storage system, I would open it up. Maybe this is a good startup idea. If anyone wants to join a startup, I'll be happy to help. Yes, please.
So right now we're talking about getting it adopted, right? So making it appear more attractive so that people want to use it. If theoretically, if you didn't have to worry about that, if you weren't worried about people actually wanting to use it, what are some things that you would change in host processors to make them more amenable for working with them?
Yeah, that's a good question. I mean, that's also part of the research, I think, figuring out what that is. But certainly adding instructions that can be executed on the memory side, better communication with the memory controller, offloading support to the memory controller. I think all of these would help. Yeah. Right now, instructions are supposed to be executed in the ALUs, right? But having some instructions that can be executed on the memory side would help. Yeah, and the memory controller support would help, certainly. I think in the processor side, I would certainly start with the memory controller. Just have the ability to execute some functions in the memory controller and offload things to the memory controller. That's relatively easily doable because it's within the domain of this chip, right? That is designed by only one company, well, a given company. That gets you near memory. Yeah. Okay, these are great questions. Yes. Yeah, runtime. I mean, there are some papers. This not a whole lot, I would say. I think this Tom paper that we did with NVIDIA is an example. Transparent offloading and mapping. I would look at that one. That's really looking at how to do the runtime a little bit. But I think there needs to be more. We had a PACT 2006 paper on GPU scheduling also. That's specific to GPUs. But those are also runtime papers. Maybe there are more that I'm not aware of. That's also possible. Okay. Okay, then let's move on. So let me give you some examples. So I think the good news is some things are happening in industry today. So this is UpMem's processing engine. These are real DIMMs that are capable of computation. They have some area overhead, but they exist. We have access to them, and we can execute real workloads in them. So this is what it looks like, basically. This is a 64 megabyte DRAM bank. Next to it, you have a processor. And this is a multi-threaded processor, 14-stage pipeline, I believe. It has an instruction memory and scratchpad data memory. So basically, it's what you're used to, let's say, as a processor. And you can program it with some C level, modified C. So it's not that bad to program also, frankly. So it's possible to actually do programming on this one. And that's what we've been doing. We've been also, Juan, for example, has been leading this effort in my group. We've been also giving tutorials on this. Actually, we will have a tutorial at HPCA in Montreal very soon. Very soon, meaning I think February, yeah. Yeah. So this is, I think, interesting. And if you're interested, there are a lot of talks that Juan delivered you can take a look at. There are some interesting things over here. Computation is not cheap, basically. You're compute bound. For example, the frequency of the processing engine is about 450 megahertz, as opposed to, let's say, 5 gigahertz today, right? So computation is very expensive. And also, because of their design choices, they don't have floating point operations. They don't have multiplications that are wider than 8 bits. For example, some things are really hard to, or slow to do. So the part of your workload that you should offload to these processors has to be really, really memory bound in that sense. So that's the key takeaway. Will this evolve in the future? Probably yes. But I think the way they designed this is it's designed inside the DRAM chip, and fundamentally, the DRAM chip fabrication is optimized for the capacitor and not logic. As a result, some of these are very difficult to overcome. I think 3D stacking technologies will overcome this because you have a separate logic die than DRAM die, and they can be designed completely separately from each other. But this is actually a good effort, in my opinion. Even then, we see some workloads that actually are quite good compared to existing CPUs and GPUs. So, for example, these are more UpMem suitable workloads where we outperform the CPU and GPU once we offload them, or once you optimize them and offload them to the UpMem. But there are some workloads that are terrible, as you can see over here, right? Some of them lose performance significantly compared to existing CPUs and GPUs. So basically, even with the downsides of this architecture, you get significant performance benefits on some workloads. I think that's a good sign. Why? Because you minimize the data moment, and data moment dominates performance as well as energy. So basically, but then workloads need to fit, as you can see over here. So the other takeaway is one of the design decisions they made in this architecture is there's no communication between different banks. So you have different processors distributed across banks. They cannot communicate with each other. Not only that, they have to communicate with each other going through the CPU, which is terrible, clearly, right? So this kills a huge fraction of the workloads from being suitable for this architecture. So you can see that this is a prototype. Some of the design choices that are made are not that amenable to, let's say, general adoption. But I think over time, hopefully, people will realize that, okay, it's a good idea to have communication between these different banks, right? I actually believe that that's really important. You need to communicate between processors so that you can, right now, basically, the workloads that are really suitable for this are workloads that are not communicating with each other. You just use these processors as parallel processors that do not communicate with each other at all. Because once you go through the communication, if you need to communicate, you have to go through the CPU, which is really bad. That's what you were trying to avoid in the first place, right? Yeah. I mean, there's another design choice that hopefully should be eliminated in future incarnations of this, which is this is really an accelerator model, like a true accelerator device model. This is not main memory. You cannot use these memories as main memory. At the same time, computation devices. So main memory is somewhere. You move the data from that main memory to this computation device, which happens to be processing in memory. And then you move the result back to main memory. That's another not so great design choice, in my opinion. Yes.
And that would include the CPU.
Yeah, that goes to the CPU also. Yes, exactly. Because there's no direct communication between the memories, right? Yeah. So even with that, basically, we see that some workloads benefit a lot. So you can imagine how bad these, how each of these design decisions kill some of the workloads. But even then, we see some workloads that benefit a lot. Okay, and if you're interested, there are papers that we have written. This is a shorter version of this paper. And we also open source some of the workloads. And we're going to add more workloads over here that we use to evaluate these systems. They're all open source, as I said. And this is a longer version of this paper if you're interested. And there are many talks about this. You can find them. More recently, we've been looking at machine learning training of some machine learning workloads, not the neural networks, because neural networks are clearly need the multiplication, let's say, which these systems don't support very well, but k-means clustering, for example, decision trees, etc. And we fit them to this architecture. To be able to do that, you need to go through a lot of pain, like optimize data representation, use lookup tables to implement complex functions, and optimize data placement and layout. And once you do that, we actually see large speedups compared to CPUs and GPUs. So again, this system, despite all of its downsides, some workloads fit nicely. Now imagine if you actually did the right design choices or better design choices, and if you improve it over time, I believe all of these numbers will improve. So I think maybe this kind of answers your question, right? These systems exist and hopefully people will latch onto them over time. Okay, yeah, so if you're interested, Juan has given talks on machine learning training. We have also looked at the tough workload, which is sparse matrix rate multiplication. This is really a tough workload for UpMem system because multiplication is a tough workload to begin with for this, and sparsity makes it even worse. And we have released essentially a sparse P library that consists of 25 SPMV, sparse matrix vector multiplication kernels. Each of them differs in terms of the compression that employ, data type that employ, data partitioning, synchronization, load balancing. So if we look at all of these effects actually on the architecture, and we compare to CPU and GPU systems, it doesn't outperform CPU and GPU, even if you optimize all of these. But it reduces data movement significantly. So the reason it does not perform is multiplication is very expensive in this system. But I think this sort of studies to stress the system are really important to do also. And you can, again, take it and play with it if you're interested. And you can find Christina's videos on this also. So other accelerators, I think, are coming. I hope these will be made public at some point or sold. I don't know. I don't know their plans clearly, but good. It's good that Samsung developed this machine learning accelerator. You can see that this is based on 3D stacked memory, HBM. And you can see that this is a completely different design point. They add floating points, multiplication and additions. In fact, that's the main thing that they execute over here. And this is real, according to them. This is their instruction set architecture, if you will. And this is a real chip implementation. Again, I don't have enough information. They've written papers about it. You can read their papers. They show good results. But again, these remain to be seen in the real world, I think. It's just Samsung's result right now. It's not some independent people's results on Samsung hardware. Samsung and Facebook together designed this recommendation system. Again, they have processing capability over here in this buffer. So this is near memory again, right? Not inside the DRAM chip. The other one was inside the DRAM chip. But they basically need a lot of memory for recommendation inference, DLRM in this particular case for Facebook. And again, they have good results in that paper that I referenced down there. SK Hynix, actually, I think this is a more aggressive accelerator on GDDR6. They've designed something similar to Samsung's FIMDRAM machine learning accelerator. And again, they have good results in their paper. Alibaba also, as I said, these are all DRAM based. That's the interesting part, right? These prototypes are all DRAM based, and people are not afraid of modifying DRAM, as you can see. At least we've overcome that hurdle. Right now, people are modifying DRAM and just putting computation. That's the good part. Yeah, I think it's also interesting. I don't think they have full results over here, but it's good to look at. It's a circuit level paper. Okay, so one question is what part of the workload should be executed where? And we've been developing some methodology to actually enable this. This is a paper that we've written. I'm going to talk about this a little bit. But basically here in this paper, we analyzed lots of applications from many different domains. And we basically quantified, we basically developed a methodology to categorize functions. I think we had 77,000 functions. And then we categorized those functions in terms of what are their bottlenecks. And based on 3 different metrics, last to first miss ratio, MPKI, misses per kilo instruction, and arithmetic intensity, you can categorize the workloads into one of 6 bottleneck classes over here. This is compute bound over here. And these are different memory bound, different types of memory bound, let's say, or L1 cache bound, for example, L1 cache capacity bound, L3 cache contention bound. So if you actually understand these different memory bottlenecks, you can develop different techniques. So for example, the first one can be alleviated with near memory processing very well. But you could also develop prefetching techniques that can take advantage of this. So this sort of categorization is actually useful. And we show some of that in the paper. So I think this sort of methodology is really important to develop. Again, we open source it. People can build on it if they're interested. And we open source the benchmark suite also. There are a lot of workloads over there and the entire tool chain. I think automating this is actually going to be important for future systems. Okay, so there's more and the paper is here. So I'm almost at the end. I think we want fundament, the energy efficient, as well as fundament, the high performance architectures. And I think data-centric architectures don't make it as a trade-off. They improve energy efficiency and performance at the same time by minimizing data movement as much as possible. So there's more in this other tutorial, but I think we've covered a lot. Maybe this is longer than this tutorial. Sorry, these slides should go away. I think I gave a longer tutorial at Samos. It was like 5.5 hours in the Samos Island, but that's not online yet. Okay, so let me conclude. I think it's clear, hopefully, that we must design systems to be balanced, high performance, energy efficient, all at the same time. Hopefully, this will lead to more intelligent systems. I've covered the data-centric part of it, but I believe systems also need to be data-driven and data-aware, as we discussed earlier. I think this requires enabling computation capability inside and close to memory structures, which is really dominating all of our system, basically. Inside and close to all of our system, let's say. This can lead to orders of magnitude improvement. I think I've shown you some results showing that. I believe this can also enable new applications and computing platforms. I believe there's a huge opportunity in medical devices, genomics. I cannot prove this claim, but I think it's possible. I also believe that this can enable a better understanding of nature. I'm going to mention this a little bit because I don't think nature is compute-centric, let's say. It's very, I believe it's data-centric, data-driven, and data-aware at the same time, actually. And who knows what else. So I think the future is bright, but we really need to do the hard work. I think we, as researchers and designers, we should do research and design, ignoring the business constraints. Let someone else see the light somehow. They will eventually see it probably, or maybe never, who knows. But we do need to do the research and design. So I will mention this thing. This is a part of nature, clearly. And everything we know about this thing is not compute-centric, right? In fact, we are using some of the principles that this uses, heterogeneity, for example. But if you look at this, computation and memory are immersed with each other somehow, in a way that we don't completely understand also at a fundamental level. But we somehow understand that it's a distributed system that has computation and memory immersed with each other. Maybe we should take more inspiration out of this. Okay, but then we need to revisit the entire stack. Okay, there's some good principles that we need to employ, but more than anything else, we need to open our minds, in my opinion. So I will acknowledge people who funded this research. There's actually a lot of companies that are interested in this research and they fund this and they want to see something happening in this direction. But we will see if something happens, really. Most importantly, I should thank my group because they're the ones who did this work. I'm just speaking for them, let's say, and guiding them a little bit. And these are some faces that have done some of this work. These are some newer faces. And we have some newsletters if you're interested in reading them. As I said, almost everything that I discussed, especially the newer works, are open source, but the papers are all out there. And we have a GitHub. You can download some of them. For example, the move is here, PIM benchmarks here. We have a emulator PIM also, that PIM simulators. So we open source as much as possible, because I think that's really important actually for adoption as well. if you want to know more about some of these papers, we organize a special session at ISVL site that covers, I think, 9 different works and in more detail. You can find it online on this YouTube page. And again, as I said, we cover a lot of this on our courses. You're welcome to attend them on YouTube. They're all live streamed. You can ask questions. I think you attended them sometimes, right? Yeah, I saw that. Yeah, I saw some comments from you. Yeah. Was it good? Hopefully it was worth your time. Yeah, that's right. That's right. Yeah, of course. Well, we have specialized. So this is the graduate level course. This is the undergraduate level course. But as I said, we have specialized PIM course. And that's growing. I think that's really useful for getting things adopted also. We cover as new as possible things over here in the PIM course. But we also have genomics courses, heterogeneous systems, hardware, software, co-design, solid-state drives. And we'll cover increasingly more solid-state drives and storage, because I actually believe that we need to do a whole lot more on the storage space in general as the research community. And there's more on the DRAM side also. Okay, I think this is where I will end. I don't know if I'm out of time, but I'm happy to take more questions. Well, we're right on time, I think, 17:45. That's not bad. But feel free to ask more questions.